Hey there, welcome to the channel. If you're new, feel free to hit that like and subscribe button so you never miss a tutorial now. Find a cozy spot where you can relax. Let your body sink into the comfort of your favorite chair or bed. Close your eyes if you like, and let the gentle rhythm of this tutorial start to wash over you. We'll be learning Python together, but at a pace that's perfect for winding down and drifting off into a peaceful sleep. So sit back, breathe easy, and let's begin. Python is a high-level, interpreted programming language that is designed to be both powerful and easy to read. It was created by a Dutch programmer named Guido van Rossum in 1991, and since then, it has grown into one of the most popular languages in the world. The language is known for its readability, which means that even complex tasks can be expressed in a way that is clear and straightforward. This makes Python an excellent choice for beginners and experts alike. Its versatility allows it to be used in a wide range of applications, from building websites and mobile apps to analyzing large data sets and creating machine learning models. Python supports multiple programming paradigms, including object-oriented programming, where you work with classes and objects, and functional programming, which focuses on using functions to structure code. This flexibility makes Python a go-to language for solving a variety of problems. One of the standout features of Python is its easy-to-learn syntax, which minimizes the amount of boilerplate code required compared to other languages. This means that you can write clean, concise code that is both efficient and readable. Python is also cross-platform, which means that the same code can run on different operating systems like Windows, Mac OS, and Linux without requiring major changes. The language comes with a large standard library, which provides built-in modules for tasks like file handling, networking, and data manipulation. Additionally, there are countless third-party packages available through the Python package index, which can be installed using pip. Python uses dynamic typing, so you don't need to explicitly declare the data type of a variable, and it automatically manages memory, freeing you from the burden of manual memory allocation. The strong community support and extensive documentation make it easier for developers to find solutions to problems, learn new concepts, and stay updated with the latest trends. To begin working with Python, you first need to download and install it from the official website, which is python.org. Once installed, you can choose an integrated development environment, or IDE, to popular options include PyCharm, which is specifically designed for Python development, Visual Studio Code, a lightweight and highly customizable editor, and Jupyter Notebook, which is ideal for data analysis and interactive coding. After installation, it's important to verify that Python is correctly set up by opening a terminal or command prompt and typing commands like Python version or Python 3 version. These commands will display the installed version of Python, confirming that the installation was successful. In addition to the core Python installation, you may want to install tools like pip, which is used to manage third-party packages, and virtual environments, which allow you to create isolated spaces for different projects to avoid conflicts between dependencies. The first step in installing Python is to visit the official download page at Python.org download and select the latest version of the language. The installation process varies slightly depending on your operating system, but the website provides detailed instructions for each platform. It's crucial to ensure that Python is added to your system's path during installation. This allows you to run Python commands from any location in the terminal or command prompt without specifying the full path to the Python executable. Once the installation is complete, you can test it by opening a terminal or command prompt and typing a simple command like print hello world. If everything is set up correctly, this will output the text hello world to the screen, confirming that Python is working as expected. Configuring your development environment is an essential step in ensuring a smooth coding experience. Start by selecting an IDE or text editor that suits your needs. For example, Visual Studio Code is a popular choice because it is free, lightweight, and offers a wide range of extensions. PyCharm is another option, especially for those who prefer a more specialized environment for Python development. Once you have chosen your editor, install any necessary extensions that enhance your workflow, such as the Python extension for syntax, highlighting, linting, and debugging. To keep your projects organized, it's a good idea to set up a virtual environment for each project. This can be done by running a command like Python mvenvenv, which creates a new environment, and then activating it using the appropriate command for your operating system. Finally, make sure your code editor has features like syntax highlighting, auto-completion, and debugging tools to make writing and testing code more efficient. Before diving into complex projects, it's important to understand the basics of Python programming. Variables in Python are used to store data, and they can hold different types of values, such as numbers, strings, or lists. For example, x equals 5 assigns the integer 5 to the variable x, while name equals John stores the string John in the variable name. Control structures like if statements for loops. And while loops allow you to make decisions and repeat actions based on certain conditions, functions are blocks of code that perform specific tasks and can be reused throughout your program. You define a function using the def keyword, followed by the function name and a set of parentheses. Built-in data structures like lists, tuples, dictionaries, and sets are used to store collections of data. Lists are ordered and mutable. Tuples are similar but immutable. Dictionaries store key-value pairs, and sets contain unique elements. Comments in Python are used to explain code and are created using the hash symbol for single-line comments or triple quotes for multi-line comments. These elements form the foundation of Python programming and are essential for writing effective and maintainable code. In summary, Python is a powerful and versatile programming language that is accessible to beginners, while also offering advanced features for experienced developers. Setting up the right environment is crucial for a smooth development experience, as it ensures that you can write, test, and debug code efficiently. Mastering the basics, such as understanding variables, control structures, functions, and data structures, is essential for building more complex programs. Regular practice is key to improving your skills, as coding is a hands-on activity that requires consistent effort. Whether you're interested in web development, data science, automation, or artificial intelligence, Python provides the tools and community support needed to succeed. By continuing to explore and experiment with Python, you can unlock its full potential and become a proficient programmer. Python uses indentation to define code blocks instead of braces. This means that the spacing before your code lines determines which group of statements belong together. For example, in an if statement, the code inside the condition must be indented to show it is part of that block. Case-sensitive variable names are another important rule. A variable named myvar is different from myvar, so you must be careful with capitalization. Comments in Python start with a hash symbol for single-line comments, which are useful for explaining specific lines of code. For longer explanations, triple quotes can be used to create multi-line comments. Additionally, statements in Python typically end with a new line, but you can use a semicolon to separate multiple statements on the same line. Consistent indentation is crucial in Python to maintain the structure of your code. The most common practice is to use 4 spaces for each level of indentation. This helps make the code readable and avoids errors. For instance, if you write an if statement, the code inside that block must be indented. If you accidentally mix different indentation levels, Python will throw an indentation error, which can be frustrating to debug. Always ensure that your indentation is uniform throughout your code to prevent such issues. Variables in Python are dynamically typed, which means you do not need to declare their type explicitly. You can assign a value to a variable, and Python will automatically determine its data type. Common data types include integers, floating point numbers, strings, Boolean values, lists, and dictionaries. When naming variables, you must follow specific rules. Variable names can start with a letter or an underscore, but cannot begin with a number or special characters. This helps avoid conflicts with Python syntax and ensures your code runs smoothly. Inline comments in Python start with a hash symbol and are used to explain specific lines of code. For example, you might write x equals 5 followed by a hash symbol and a comment to clarify its purpose. Docstrings, which are enclosed in triple quotes, serve a different role. They are used to document functions, classes, or modules, and can be accessed later for help documentation. This makes your code more understandable for others and for yourself when you return to it later. Proper use of comments and docstrings is essential for writing maintainable code. The basic structure of a Python program begins with importing necessary modules or libraries. For example, you might import the math module to access mathematical functions. Functions are defined using the def keyword, followed by the function name and parentheses. Control structures like if, for, and while statements allow you to manage the flow of your program. For instance, a function called greet could take a name as an argument and print a personalized message. This structure forms the foundation for more complex programs and helps organize your code logically. By now, you have learned the fundamental syntax rules of Python, including indentation, variable naming, and commenting. you understand how to structure basic programs using imports, functions, and control structures. These concepts are essential for writing clean, efficient, and readable code. With practice, you will be able to create more advanced programs and build a strong foundation in Python programming. Keep experimenting and applying these principles to improve your skills. Variables are like containers that hold data values in Python. When you assign a value to a variable, you use the equals sign operator. For example, x equals 5. This means the variable x now stores the number 5. Variable names must follow specific rules, such as starting with a letter or an underscore, and they can include numbers and underscores, but cannot start with a number. It is also important to avoid using reserved keywords like if or for as variable names. One of the key features of variables in Python is that they can be reassigned to new values at any time, allowing for dynamic and flexible data handling. Python has several built-in data types that define the kind of data a variable can hold. These include integers, which are whole numbers like 25, floats, which are decimal numbers like 9.99, strings, which are sequences of characters enclosed in quotes like Alice, and booleans, which represent true or false values. Understanding these data types is essential because they determine the operations you can perform on the data. For instance, you can add integers and floats together, but you cannot directly add a string and a number without converting one of them. Each data type has its own characteristics and uses, making it easier to manage and manipulate data in programs. Integers are whole numbers that can be positive, negative, or 0, such as 10. Floats, on the other hand, are numbers with decimal points, like 3.14. Strings are used to store text and are always enclosed in either single or double quotes, for example, hello. Booleans are logical values that can only be true or false, often used in conditions and comparisons. These data types are fundamental to programming because they allow you to represent and work with different kinds of information. For instance, a Boolean variable might be used to check if a user is logged in, while a string could store a person's name. When naming variables in Python, there are specific rules to follow. Variable names must start with a letter or an underscore, but they cannot start with a number. It is also crucial to avoid using reserved keywords, which are words that have special meanings in Python, such as if, for, or while. readability and consistency, it is common practice to use lowercase letters and underscores to separate words in variable names, following the snake case convention. For example, a variable named username would be written as username. This helps make the code easier to understand and reduces the likelihood of errors. Type conversion in Python allows you to change a value from one data type to another using built-in functions. For instance, the int function can convert a string like 100 into an integer, while the float function can turn a string into a decimal number. Similarly, the str function converts other data types into strings. This is particularly useful when you need to combine different types of data, such as adding a number to a string. However, not all conversions are possible, and attempting to convert incompatible types can result in errors. Understanding type conversion helps ensure that your programs handle data correctly and avoid unexpected issues. In summary, variables are essential for storing and managing data in Python. Choosing the right data type ensures that your program behaves as expected and performs operations correctly. Following variable naming rules improves code readability and prevents conflicts with Python's reserved keywords. Additionally, type conversion allows you to work with different data types flexibly. To reinforce these concepts, practice by writing simple variable assignments and checking their types. This hands-on approach will help solidify your understanding and make you more confident in using Python for programming tasks. Good morning. Today, we will explore the basics of numbers in Python. Python supports two main types of numbers: integers, which are whole numbers like 5 or -3, and floating point numbers, which include decimal points such as 3.14 or -0.5. These numerical types form the foundation for performing calculations, analyzing data, and conducting scientific computations. To determine the type of a number, you can use the built-in function called type. For example, if you type 5, Python will return int, indicating it is an integer. Similarly, type 314 will return float, showing it is a floating point number. Understanding these data types is essential for writing accurate and efficient code. Now let's discuss the arithmetic operators in Python. The basic operators include plus for addition, minus for subtraction, asterisk for multiplication, and slash for division. In addition to these, there are other operators, such as percent for modulus, which gives the remainder of a division, double asterisk for exponentiation, which raises a number to a power, and double slash for floor division, which divides and rounds down to the nearest integer. For instance, 5 plus 3 equals 8, and 10 mod 3 equals 1. These operators allow you to perform a wide range of mathematical operations, making Python a powerful tool for numerical computations. Next, we will look at the order of operations in Python. The language follows the PEMDAS rule, which stands for parentheses, exponents, multiplication and division, and addition and subtraction. This means that expressions inside parentheses are evaluated first, followed by exponents, then multiplication and division from left to right, and finally addition and subtraction from left to right. For example, 3 plus 5 multiplied by 2 equals 13, because multiplication is performed before addition. However, if you use parentheses, such as 3 plus 5, enclosed in parentheses multiplied by 2, the result becomes 16. Using parentheses effectively can help you control the flow of calculations and avoid unexpected results. Let's now explore the built-in functions available for working with numbers. The abs function returns the absolute value of a number, which is its distance from 0 on the number line. For example, abs negative 5 equals 5. The round function rounds a number to the nearest integer, so round 3.7 becomes 4. For more advanced mathematical operations, Python provides the math module, which includes functions like square root. For instance, math square root of 16 equals 4.0. These functions are invaluable for tasks ranging from simple calculations to complex scientific computations. Handling user input is another crucial aspect of working with numbers. The input function allows you to prompt the user for information, but it always returns a string. To convert this input into a number, you can use the int function for integers or the float function for decimal values. For example, if you ask the user to enter their age, you can store it as an integer by writing age equals int input with the prompt enter your age. This approach enables you to create interactive programs that respond to user-provided data. When working with numbers, it's important to be aware of common errors and how to address them. One such error is division by 0, which occurs when you try to divide a number by 0. This will cause your program to crash, so always check that the denominator is not 0 before performing division. Another issue is type conversion errors, which happen if the input cannot be converted to a number. For example, if a user enters a letter instead of a number, the int function will throw an error. Additionally, floating point numbers can sometimes lead to precision issues, such as 0.1 plus 0.2 not equaling exactly 0.3. To mitigate this, you can use the round function to limit decimal places, or the decimal module for higher precision. In conclusion, mastering arithmetic operations and number types is essential for effective Python programming. By leveraging built-in functions and handling user input, you can create dynamic and responsive programs. Remember to practice with real-world examples to solidify your understanding. Whether you're solving mathematical problems, analyzing data, or building applications, a strong grasp of numbers in Python will serve you well. Keep experimenting and applying these concepts to enhance your skills. Thank you. Strings are sequences of characters in Python. They can be created using single quotes, double quotes, or triple quotes for multi-line strings. For example, hello or Python are simple strings, while multi-line string allows for text spanning multiple lines. One important thing to note is that strings are immutable, which means once they are created, their content cannot be changed. This has implications for how we manipulate strings, as any modification creates a new string instead of altering the original. Understanding this helps avoid unexpected errors in code. Strings have several properties that make them versatile. Indexing allows you to access individual characters by their position, starting from 0. For instance, if a string is Python, the first character P is at index 0. Slicing lets you extract parts of a string, like S1, for which would give ith from Python. The length of a string can be determined using the len function, which returns the total number of characters. Concatenation is another key property, where you can combine strings using the plus operator, such as hello plus world, to create hello world. These properties form the foundation for more complex string operations. There are many built-in string methods that help manipulate and analyze text. The lower method converts all characters to lowercase, while upper does the opposite. Strip removes leading and trailing white space, which is useful for cleaning user input. Replace allows you to swap out specific substrings, like changing hello to hi in a sentence. The find method locates a substring within a string and returns its starting index, which can be helpful for searching or parsing text. These methods are essential for tasks like data cleaning or text processing. String formatting is a powerful way to embed values into strings dynamically. F-strings, introduced in Python 3.6, offer a clean and readable syntax, such as f-hello name, where name is a variable. The format method provides similar functionality with a slightly different syntax, like hello, format name. Another older approach uses the percent operator, as in hello %s %name, while f-strings are now preferred for their clarity. Understanding all methods is useful when working with legacy code or specific use cases. Manipulating strings often involves splitting them into parts or combining elements. The split method divides a string into a list based on a delimiter, such as splitting apple, banana, orange into apple, banana, orange. The join method does the reverse, combining list elements into a single string with a specified separator. Checking a string's content is also common, with methods like isAlpha to verify if all characters are letters, or starts with to check for a specific prefix. Case conversion methods like capitalize, title, and swap case allow for adjusting text formatting to meet specific requirements. Practical applications of strings are everywhere. For example, validating user input might involve checking if a string is alphanumeric using isalnum. Processing text data could mean removing punctuation or normalizing case. Formatting output is crucial for presenting data clearly, such as displaying currency values or dates. A common example is cleaning a string by stripping white space, converting it to lowercase, and replacing spaces with underscores, as in cleaned equals s-strip lower a place. These techniques are vital for tasks like data preprocessing or generating user-friendly messages. In summary, strings are a fundamental part of Python programming, especially for handling text. Mastering their properties and methods enables efficient data manipulation and analysis. Practicing with real-world scenarios, like processing user input or formatting output, reinforces these concepts. For more advanced tasks, exploring topics like regular expressions can unlock powerful text processing capabilities. By understanding and applying these techniques, you'll be well equipped to tackle a wide range of programming challenges. User input and output are fundamental components of any Python program. They allow our code to interact with users, making programs dynamic and responsive to real-world data. Without input, programs would be static, unable to adapt to different scenarios. Output, on the other hand, ensures users receive meaningful feedback from the program. The two key functions we will explore today are input and print. The input function captures data from the user, while the print function displays results. Together, they form the backbone of user interaction in Python. To collect data from users, we use the input function. Its syntax is simple. A variable stores the result of input, followed by a prompt message in quotes. For example, name equals input with the message, enter your name. This prompt guides the user on what to enter. It is important to note that input always returns a string, regardless of the data type. Even if a user enters a number, it is treated as text. This behavior is crucial to remember, as it affects how we process and use the data later. While input returns strings, many programs require other data types like integers or floats. To achieve this, we use conversion functions. For instance, age equals int input with the message, enter your age. This converts the string input to an integer. However, invalid inputs, such as letters instead of numbers, can cause errors. Therefore, we must handle these cases. Best practices include validating input before processing. For example, checking if the input is numeric before conversion. This ensures our programs are robust and user-friendly. Displaying output is equally important. The print function outputs messages or variables. Its syntax is straightforward. Print with a string or variable. For example, print hello or print name. To make output more readable, we use f-strings. An f-string allows embedding variables directly in the string, like f-hello, name. This is more efficient than concatenation. Additionally, we can format output by adding line breaks or separators. For example, print with a comma adds a space, while the end parameter controls what follows the output. These techniques enhance clarity and usability. Let's look at a practical example. A simple program collects a user's name and age, then displays a formatted message. The code starts by prompting for the name using input, then converts the age input to an integer. Finally, it prints a message combining both variables. This demonstrates input validation and output formatting. For instance, if the user enters a non-numeric value for age, the program may crash. To prevent this, we would add error handling. This example highlights how input and output work together to create interactive programs. Common pitfalls in input and output include forgetting to convert data types, leading to type errors. For example, adding a string and an integer would cause an error. To handle invalid inputs, we use try-except blocks, which catch exceptions and prevent program crashes. Syntax errors, like missing parentheses in print statements, are also frequent. Python 3 requires parentheses, so missing them causes errors. Lastly, comments in code improve readability, especially in complex outputs. They explain the purpose of each line, making the code easier to understand and maintain. Mastering input and output is essential for creating interactive Python programs. Practice using input and print with various data types to build confidence. Apply best practices like validating input and handling errors to ensure robust code. As you progress, these skills will prepare you for advanced topics like file I/O and data processing. Remember, effective user interaction is the key to developing functional and user-friendly applications. Keep experimenting and refining your techniques. Conditional statements are a fundamental concept in programming that allow programs to make decisions based on specific conditions. These statements enable the program to choose between different paths of execution, depending on whether a condition is true or false. By using Boolean values, which can only be either true or false, we can control the flow of our code dynamically. The key keywords in Python for implementing conditional statements are if, elif, and else. The if statement checks a condition, and if it is true, the associated code block is executed. The elif statement allows for checking additional conditions if the previous ones are false, while the else statement serves as a default option when none of the previous conditions are met. These constructs are essential for creating responsive and flexible programs that can adapt to various scenarios. The syntax for conditional statements in Python is straightforward, but requires careful attention to structure. The if statement begins with the keyword if followed by a condition, which is a Boolean expression. If the condition evaluates to true, code block indented beneath the if statement is executed. The elif statement, short for else if, is used to check another condition if the previous if or elif conditions are false. This allows for multiple checks in a single conditional structure. The else statement is placed at the end of a chain of if and elif conditions and executes only if all previous conditions are false. Each of these statements must be followed by a colon, and the code blocks they control must be properly indented to ensure the program runs as intended. This structure ensures clarity and readability in decision-making logic. Let us look at a simple example of an if statement. Suppose we want to check if a number is positive. We start by assigning the variable num the value of 5. Then, we use the if statement to evaluate whether num is greater than 0. If this condition is true, the code block under the if statement is executed, which in this case prints the message positive number. Since 5 is indeed greater than 0, the output of this code will be positive number. This basic example demonstrates how conditional statements can be used to make decisions based on numerical values. It is a foundational concept that can be expanded to handle more complex scenarios. Now, let us examine an if-else statement. This structure allows us to handle two possible outcomes of a condition. For instance, we can determine whether a number is even or odd. Assign the variable num the value of 4. Using the if statement, we check if num modulo 2 equals 0. If this condition is true, the code block under if executes, printing even. Otherwise, the else block runs, printing odd. Since 4 divided by 2 leaves no remainder, the condition is true, and the output is even. This example highlights the utility of if-else statements in scenarios where there are two distinct possibilities. It ensures that every possible case is accounted for, providing a clear and concise way to handle binary decisions. Next, we explore an if-elif-else chain, which is useful when there are multiple conditions to check. For example, let us evaluate a student's score to determine their grade. Assign the variable score the value of 85. The first condition checks if the score is greater than or equal to 90. If true, the code prints A. If not, the elif condition checks if the score is greater than or equal to 80, printing B. If neither condition is met, the else block executes, printing C. Since 85 is less than 90, but greater than 80, the output is B. This structure allows for a sequence of checks, making it ideal for scenarios where multiple criteria must be evaluated in order. It helps avoid nested conditions and keeps the code organized. Nested conditional statements allow us to check multiple conditions within a single block of code. For example, consider determining voting and drinking eligibility based on age. Assign the variable age the value of 20. The outer if statement checks if age is greater than or equal to 18. If true, the inner if statement checks if age is greater than or equal to 21. If this condition is true, the code prints eligible for voting and drinking. If not, the else block under the inner if statement executes, printing eligible for voting. Since 20 is less than 21, the output is eligible for voting. This example demonstrates how nested conditions can handle layered decision-making, though it is important to balance complexity with readability. When working with conditional statements, there are several common mistakes to avoid. One frequent error is forgetting to include a colon after the condition, which is required in Python syntax. Another mistake is using the assignment operator equals instead of the comparison operator equals, which can lead to logical errors. Proper indentation is also crucial, as Python uses it to define code blocks. If the indentation is incorrect, the code may not execute as intended. Lastly, failing to include an else clause can leave some scenarios unhandled, leading to unexpected behavior. By being mindful of these pitfalls, we can write more reliable and error-free code. To write effective conditional statements, there are several best practices to follow. First, use elif statements for multiple conditions instead of nesting if statements, which can make the code harder to read. Keep conditions simple and avoid overly complex expressions, as this improves readability. Adding comments to explain complex logic helps others understand the purpose of each condition. Finally, test all possible branches of your code to ensure it behaves correctly in every scenario. These practices not only enhance the clarity of your code, but also make it more robust and easier to maintain. In conclusion, conditional statements are a cornerstone of programming, enabling programs to make decisions based on logical conditions. By mastering the use of if, elif, and else, we can create dynamic and responsive code that adapts to different inputs and situations. Practicing the implementation of these statements helps solidify their concepts and improves problem-solving skills. Applying them to real-world scenarios allows us to build practical solutions that address specific needs. As you continue to explore programming, remember that conditional logic is a powerful tool that can transform simple code into sophisticated applications. Loops are essential in programming because they allow us to repeat a block of code multiple times. This repetition is crucial for automating tasks that would otherwise require writing the same code over and over again. There are two main types of loops in Python: for loops and while loops. For loops are typically used when we know the number of iterations in advance, such as when we want to loop through a list of items or generate a sequence of numbers. While loops, on the other hand, continue executing as long as a specific condition remains true. Both types of loops play a vital role in making Python programs efficient and dynamic. Whether you're processing data, managing user input, or performing complex calculations, loops are a fundamental tool that every Python programmer must master. The primary purpose of loops is to reduce code redundancy by allowing us to execute a block of code repeatedly without duplicating it. This is especially useful when working with sequences like lists, tuples, strings, and other iterable objects. For example, if you have a list of names, a loop can iterate through each name and perform an action, such as printing or modifying it, without needing to write separate lines for each element. Loops also help control the flow of a program by enabling decisions based on conditions. Imagine a scenario where a program needs to keep asking a user for input until they provide the correct answer. A loop can handle this by repeatedly checking the input against a condition. By using loops, we can create more flexible and efficient programs that adapt to changing situations. The syntax for a for loop in Python is straightforward. It begins with the keyword for, followed by a variable that represents each item in the iterable. The structure is for variable in iterable, and then a colon. For example, a for loop might look like for I in range 5, which means the variable I will take on the values 0 through 4. The code block under the for loop is executed once for each item in the iterable. The range function is commonly used with for loops to generate a sequence of numbers. However, for loops can also iterate over other data structures, such as lists, tuples, and strings. If you have a list of numbers and want to perform an operation on each, a for loop makes this simple and efficient. Understanding how to use for loops with different iterables is a key step in mastering Python. While loops in Python are structured around a condition that determines whether the loop continues to execute, the syntax is while condition, followed by a colon and the code block to be repeated. For instance, a while loop might check if a variable x is less than 10, as in while x 10. This loop will keep running as long as the condition remains true. However, it is important to ensure that the condition eventually becomes false, or the loop will run indefinitely, creating an infinite loop. To avoid this, programmers often include statements within the loop that modify the condition. For example, incrementing a counter variable or updating a flag. While loops are particularly useful in scenarios where the number of iterations is not known in advance, such as waiting for user input or processing data until a specific event occurs. Choosing between a for loop and a while loop depends on the specific task at hand. For loops are ideal for iterating over known sequences, such as a list of items or a range of numbers. They are concise and efficient when the number of iterations is predictable. For example, if you need to print numbers from 1 to 10, a for loop with range 1, 11 is the perfect solution. On the other hand, while loops are better suited for situations where the number of iterations is unknown or depends on dynamic conditions. Imagine a program that continues to prompt a user for a valid password until they enter the correct one. A while loop can handle this by checking the input repeatedly. Understanding when to use each type of loop is crucial for writing clean, efficient, and error-free code. For loops are commonly used in scenarios where we need to process elements in a sequence. For example, if you have a list of numbers, a for loop can iterate through each one to perform calculations, such as summing them up or checking for specific values. They are also useful for generating sequences, like creating a list of squares for numbers in a range. While loops, on the other hand, are often employed for tasks that require validation or monitoring. For instance, a while loop can repeatedly ask a user to enter a number within a certain range until they provide a valid input. Additionally, nested loops are used to handle multi-dimensional data structures, such as 2D lists or matrices. By combining loops, you can iterate through each row and column of a 2D list to perform operations like searching for a specific value or modifying elements. These use cases highlight the versatility of loops in solving a wide range of programming problems. When working with loops, it is important to follow best practices to ensure clarity and prevent errors. For predictable iterations, such as looping through a list or a range of numbers, a for loop is the best choice. It is concise and reduces the risk of infinite loops. However, for situations where the number of iterations depends on a condition that may change during execution, a while loop is more appropriate. To avoid infinite loops, always ensure that the condition eventually becomes false. For example, if you are using a while loop to count up to 10, make sure the counter increments with each iteration. Additionally, using control statements like break and continue can help manage loop execution. The break statement exits the loop immediately when a condition is met, while the continue statement skips the current iteration and moves to the next. These tools provide greater flexibility in handling complex loop scenarios. In conclusion, loops are a fundamental concept in Python programming that enable efficient automation of repetitive tasks. Whether you are working with sequences, conditions, or dynamic data, choosing the right type of loop is essential for writing effective code. For loops are ideal for iterating over known sequences, while loops are better suited for scenarios with unpredictable or conditional iterations. Practicing with examples is the best way to master loops and understand their applications. By experimenting with different data structures and conditions, you can develop a deeper understanding of how loops control program flow and enhance functionality. As you continue learning Python, loops will become an indispensable part of your coding toolkit, allowing you to solve complex problems with ease and efficiency. Functions are reusable blocks of code that perform specific tasks. Think of them as mini programs within your larger code base. They make your code easier to read, organize, and maintain. For example, instead of writing the same code multiple times, you can define a function once and call it whenever needed. Python comes with built-in functions like print, which outputs text, and len, which measures the length of a data structure. But the real power lies in creating your own custom functions to handle unique operations tailored to your needs. To define a custom function in Python, you use the def keyword followed by the function name and parentheses. The syntax is simple: def function name parentheses colon. Inside the function, you write the code that executes when the function is called. Indentation documentation is critical here because Python relies on it to determine which lines belong to the function. For instance, the greet function example shows how to print a message. When you call greet, the code inside the function runs, producing the output. This structure ensures clarity and avoids confusion in larger programs. Parameters are the variables listed in the function definition, acting as placeholders for values that will be provided later. Arguments are the actual values you pass when calling the function. There are different ways to pass these arguments. Positional arguments rely on the order you provide them, while keyword arguments use names to specify which value corresponds to which parameter. Default parameters offer a fallback value if no argument is given. For example, a function with a default parameter for a greeting can still accept a custom message when needed. Understanding these types helps make your functions flexible and intuitive. The return statement is how a function sends data back to the part of the code that called it. This allows functions to produce results that can be used elsewhere. A function can return a single value, like the sum of two numbers, or multiple values as a tuple. For instance, the add function returns the sum of A and B, which can then be stored in a variable or used in further calculations. Without return, functions would only perform actions but couldn't share their results, limiting their usefulness in larger programs. Variables inside a function exist only within that function's scope, meaning they are local and inaccessible outside. This prevents unintended changes to data in other parts of the program. However, global variables defined outside functions can be accessed anywhere. While this is convenient, it can also lead to bugs if not managed carefully. For example, modifying a global variable inside a function might have unexpected side effects. Best practices recommend minimizing global variables and using parameters and return values to pass data between functions. Let's look at a simple function example. The square function takes an input x and returns x raised to the power of 2. When you call square with 5, it calculates 5 multiplied by 5, resulting in 25. This demonstrates how functions can encapsulate a single operation and be reused with different inputs. By testing the function with various numbers, you can see how it consistently applies the same logic, making your code more efficient and easier to debug. Following best practices ensures your functions are clear and effective. Start by choosing descriptive names that explain what the function does, like calculate area instead of calc. Keep each function focused on one task to avoid confusion. Adding docstrings, which are string literals at the start of a function, helps others understand its purpose and usage. Lastly, avoid overusing global variables, as they can complicate code maintenance. These habits make your code more readable and collaborative. In conclusion, functions are the building blocks of well-structured Python programs. They help break down complex problems into smaller, manageable pieces, making your code more efficient and easier to update. By mastering custom functions, you can write cleaner, more reusable code that scales with your projects. Practice by creating functions for everyday tasks, like calculating discounts or formatting data, to reinforce these concepts in real-world scenarios. Functions in Python serve as the building blocks of code, allowing programmers to encapsulate logic and reuse it efficiently. When we talk about parameters, we are referring to the inputs that a function can take. These parameters act as placeholders that get filled with actual values when the function is called. Return values, on the other hand, are the outputs that a function can send back to the caller. This two-way communication between functions and the rest of the program is essential for creating dynamic and interactive code. Understanding how to use parameters and return values effectively is like learning the foundation of a language. It opens the door to writing modular, reusable, and maintainable code. Whether you're building a simple calculator or a complex application, these concepts are the backbone of functional programming in Python. Python functions can accept a variety of parameter types, each with its own purpose and flexibility. Positional parameters are the most straightforward, requiring arguments to be passed in the exact order they are defined in the function. Keyword parameters, however, allow you to specify values by their names, which makes the code more readable and reduces the chance of errors caused by incorrect order. Default parameters provide a safety net by assigning a predefined value if the caller doesn't supply one. This is particularly useful for optional arguments. Lastly, variable length parameters, such as args and quargs, enable functions to handle an arbitrary number of inputs, making them incredibly versatile for scenarios where the number of arguments isn't known in advance. Together, these parameter types give Python functions the power to adapt to a wide range of use cases. Positional parameters are the most common type of function arguments in Python. They rely on the order in which they are provided. For example, if a function is defined with parameters a and b, the first argument passed will be assigned to a, and the second to be this is straightforward, but also strict. Changing the order of arguments can lead to unexpected results. Consider a function like adda b that returns the sum of two numbers. Calling add2 works perfectly, but if the order is reversed, it might not cause an error, but it could lead to logical issues if the function expects a specific sequence. Positional parameters are ideal when the meaning of each argument is clear from its position, but they require careful handling to avoid confusion. Keyword parameters introduce a level of flexibility by allowing you to specify arguments by their names rather than their positions. This is especially useful when a function has multiple parameters, some of which may be optional or have similar data types. For instance, a function like greetNameMessage can be called with greetMessage equals hello, name equals Alice to ensure clarity. This approach not only makes the code more readable, but also eliminates the risk of passing arguments in the wrong order. Keyword parameters are a great tool for improving code maintainability, as they make the purpose of each argument explicit. They are particularly helpful when working with functions that have many parameters, or when some parameters have default values. Default parameters provide a way to define functions that can be called with fewer arguments, as they have predefined values. This is especially useful for optional parameters that are rarely changed. For example, a power function can be defined with a default exponent of 2, so that calling power3 returns 9 instead of requiring the user to specify the exponent each time. However, it's important to note that default values are evaluated only once when the function is defined, not each time it is called. This means that mutable default values, like lists or dictionaries, can lead to unexpected behavior if not handled carefully. Default parameters are a powerful feature for creating functions that are both simple and flexible, allowing users to focus on the most common use cases while still having the option to customize behavior when needed. Variable length parameters give functions the ability to handle an unpredictable number of arguments. The arg syntax allows a function to accept any number of positional arguments, which are then stored in a tuple. This is useful for functions that need to process a list of values without knowing how many there will be. Similarly, quarks allows a function to accept any number of keyword arguments which are stored in a dictionary. This makes it easy to create functions that can adapt to different scenarios. For example, a logging function can take multiple messages and additional details, such as a log level or timestamp, without requiring the user to specify them in advance. Variable length parameters are a key feature for writing generic and reusable code, especially in situations where the input structure may vary. Return values are the mechanism by which functions communicate their results back to the caller. When a function executes a return statement, it immediately exits and sends the specified value back to the place where it was called. For example, a square function that returns x multiplied by x will provide the result to the caller, which can then be used in further calculations. If a function does not have a return statement, it implicitly returns none, which can be useful for functions that perform actions rather than compute values. Understanding how to use return values effectively is crucial for building functions that can be integrated into larger programs, as they allow data to flow seamlessly between different parts of the code. Python's ability to return multiple values is one of its unique features. While most programming languages require you to return a single value, Python allows functions to return multiple values as a tuple. For example, a function like getCoordinates can return 10 and 20, which can then be unpacked into separate variables using x, y equals getCoordinates. This is particularly useful for functions that need to provide several pieces of information at once, such as a function that calculates both the area and perimeter of a shape. The tuple returned by the function can also be stored as a single variable if needed, offering flexibility in how the results are used. This feature simplifies the design of functions that need to return more than one value without requiring complex data structures. When writing functions, following best practices ensures that your code is clean, readable, and maintainable. First, always use descriptive parameter names that clearly indicate their purpose. For example, instead of using a generic name like x, use something like base or exponent to make the function's behavior obvious. Second, avoid overloading functions with too many parameters, as this can make them difficult to use and understand. If a function has too many arguments, consider breaking it into smaller, more focused functions. Third, prefer returning values over modifying global variables, as this keeps functions self-contained and reduces the risk of unintended side effects. Finally, document your parameters and return values in docstrings, which helps other developers understand how to use your functions correctly. These practices not only improve code quality, but also make collaboration easier. Parameters and return values are fundamental to the design of functions in Python. They allow functions to be dynamic, reusable, and adaptable to different scenarios. By mastering these concepts, you can create code that is not only efficient, but also easy to understand and maintain. Whether you're working on small scripts or large applications, the ability to pass data into functions and retrieve results from them is essential for building robust programs. As you continue to learn Python, practice writing functions with different types of parameters and return strategies to deepen your understanding. The more you experiment with these features, the more confident you'll become in leveraging them to solve real-world problems. Lists are one of the most versatile and commonly used data structures in Python. They allow you to store multiple items in a single variable, which makes them ideal for managing collections of data. What makes lists unique is that they are ordered, meaning the elements have a specific sequence, and they are mutable, which means you can change their contents after creation. This flexibility is crucial when working with dynamic data. The items in a list can be of any data type, such as integers, strings, floating point numbers, or even other lists. For example, you might have a list that contains a mix of numbers and text, or a list of lists to represent more complex structures. To create a list, you can use square brackets like this: apple, banana, cherry, or you can use the list constructor, which is useful when converting other data types into a list. Understanding how to create and manipulate lists is the foundation for many advanced programming tasks. Accessing elements in a list is straightforward, but it requires an understanding of indexing. Python uses a zero-based indexing system, which means the first element in a list is at position 0, the second at position 1, and so on. For example, if you have a list called fruits, the first element, apple, is accessed using fruits 0. This system makes it easy to retrieve specific items when you know their position. However, Python also allows you to use negative indices, which count from the end of the list. The last element in a list is at index -1, the second to last at -2, and so on. This feature is particularly useful when you want to access elements without knowing the exact length of the list. For instance, Fruits 1 would return the last item, cherry, in the example list. Mastering indexing is essential for efficiently working with lists in your code. Modifying lists is a core aspect of working with them, and Python provides several methods to add or remove elements. To add items, you can use the append method, which adds an element to the end of the list. For example, fruits, append orange would add orange to the end of the fruits list. If you need to insert an element at a specific position, the insert method allows you to do so by specifying the index. For instance, fruits insert 1, mango would place mango at the second position. Another method, extend, is useful when you want to add multiple elements from another iterable, such as a list or a string. Removing elements can be done with methods like remove, which deletes the first occurrence of a specified value, or pop, which removes an element by its index. The del statement offers even more flexibility, as it can delete elements by index, or even entire slices of the list. These tools give you powerful control over how you manage and update your data. One of the most powerful features of lists is their ability to perform operations that manipulate subsets of their elements. Slicing is a technique that allows you to extract a portion of a list using a start and end index. For example, numbers 1, 3 would return the elements at positions 1 and 2, excluding the element at position 3. This is particularly useful when you need to work with a specific range of data without modifying the original list. Concatenation is another common operation where you can combine two or more lists using the plus operator. For instance, list 1 plus list 2 would create a new list containing all elements from both. Repetition is also possible, where a list can be multiplied by a number to repeat its elements. For example, 1, 2, 2 would result in 1, 2, 1, 2. These operations make it easy to manipulate and transform lists in ways that are both efficient and intuitive. Python provides several built-in functions that make working with lists more convenient. The len function returns the number of items in a list, which is essential for determining its size. The max and min functions are used to find the largest and and smallest elements, respectively. However, these functions require that the elements in the list are comparable, such as numbers or strings. The sum function adds up all the numeric elements in a list, making it ideal for calculations. Finally, the sorted function returns a new list that is sorted in ascending order, leaving the original list unchanged. These functions are invaluable for quickly analyzing and processing data stored in lists. Understanding how to use them can save time and reduce the complexity of your code. Iterating through lists is a fundamental skill in Python programming, as it allows you to process each element in a list sequentially. The simplest way to do this is with a for loop, which cycles through each item in the list and performs an action. For example, a loop like for fruit in fruits. Print fruit would display each element in the fruits list. This is particularly useful when you need to apply the same operation to every item. Another powerful tool is the enumerate function, which allows you to track both the index and the value of each element as you loop through the list. This is especially helpful when you need to modify elements based on their position or perform actions that depend on their location in the list. These techniques make it easy to work with lists in a variety of scenarios. Nested lists are a way to create more complex data structures by embedding one list inside another. This is often used to represent two-dimensional data, such as matrices or grids. For example, a list like matrix equals 1, 2, 3, 4 creates a 2x2 matrix, where each inner list represents a row. Accessing elements in a nested list requires using multiple indices. To retrieve the number 2 from the matrix, you would use matrix 0, 1, where the first index refers to the row and the second to the column. This structure is useful for tasks like handling tabular data, where each row contains related information. Nested lists can also be more deeply embedded, such as a list of lists, allowing for even more complex data organization. Understanding how to work with nested lists is essential for handling advanced data structures in Python. List comprehensions are a concise and efficient way to create lists in Python. They allow you to generate a new list by applying an expression to each item in an iterable, such as a range or another list. The syntax is expression for item in iterable if condition, which makes it easy to write compact and readable code. For example, the list squares equals x2 for x in range 5 creates a list of the squares of numbers from 0 to 4. This approach is not only more readable, but also often faster than using traditional for loops. List comprehensions can also include conditions to filter elements, such as x for x in range 10 if x%2 equals 0, which creates a list of even numbers. By using list comprehensions, you can write cleaner and more Pythonic code that is both powerful and easy to understand. In summary, lists are a fundamental tool in Python for storing and manipulating data. They are ordered, mutable, and capable of holding a wide variety of data types, making them incredibly versatile. Key operations such as indexing, slicing, modification, and iteration allow you to work with lists in a wide range of scenarios. Nested lists and list comprehensions further enhance their flexibility, enabling you to handle complex data structures and write concise code. As you continue to learn Python, practicing with lists will help you develop the skills needed to solve real-world problems efficiently. Whether you're working with simple data or building more complex applications, lists will be an essential part of your programming toolkit. Good morning, everyone. Today, we will explore 3 essential data structures in Python: tuples, sets, and dictionaries. These structures are fundamental for organizing and managing data efficiently. Let's start by understanding their roles. Tuples are non-mutable, meaning once created, their contents cannot be changed. Sets are mutable, but store unique, unordered elements, making them ideal for tasks like removing duplicates. Dictionaries, on the other hand, store key-value pairs, allowing fast lookups and structured data storage. Each of these has distinct characteristics and use cases, so it's important to know when to use each one. By the end of this presentation, you'll have a clear understanding of their differences and how they can enhance your Python programming. Let's dive into tuples. A tuple is an immutable and ordered collection of items. This means that once you create a tuple, you cannot modify its elements. For example, you might write mytuple equals 1, 2, 3. Because tuples are ordered, you can access their elements using indexing, like mytuple at index 0, which would return 1. Slicing is also possible, such as mytuple from index 1 to 2, giving you 2 and 3. Tuples have built-in methods like count, which counts occurrences of a value, and index, which finds the position of a value. are particularly useful for storing fixed data, such as coordinates, or returning multiple values from a function. Since they are immutable, tuples are safer for data that should not change during program execution. Next, let's discuss sets. A set is an unordered, unindexed collection of unique elements. Unlike tuples, sets do not maintain a specific order, and you cannot access elements by their position. You create a set using curly braces, like my set equals 1, 2, 3. One of the key features of sets is that they automatically eliminate duplicates. For instance, if you add 3 again, the set will still contain only 1, 2, 3. Sets support operations like union, which combines 2 sets, and intersection, which finds common elements between them. You can also use methods like add to insert new elements, or remove to delete an existing one. Sets are ideal for tasks like checking membership quickly or cleaning data by removing duplicates. Their unordered nature makes them perfect for scenarios where the order of elements doesn't matter. Now let's move on to dictionaries. A dictionary is a mutable collection of key-value pairs. Unlike tuples and sets, dictionaries allow you to store data in a structured way, where each value is associated with a unique key. You create a dictionary using curly braces, such as mydict equals key value. To access a value, you use its corresponding key, like mydict at key, which returns value. Dictionaries also have methods like keys, which lists all the keys' values, which lists all the values, and items, which returns both keys and values as pairs. Dictionaries are incredibly useful for tasks like storing user data, configurations, or any scenario where you need to retrieve information quickly using a unique identifier. Their flexibility and speed make them a cornerstone of Python programming. Let's compare these 3 data structures. Tuples are immutable, ordered, and hashable, making them suitable for fixed data. Sets are mutable, unordered, and store unique elements, which is great for eliminating duplicates or checking membership. Dictionaries are mutable and optimized for lookups, using key-value pairs to store structured data. Choosing the right structure depends on your needs. If you need data that won't change, use a tuple. If you need to ensure uniqueness or perform set operations, use a set. If you need fast lookups or structured data, use a dictionary. Understanding these differences will help you write more efficient and readable code. Let's look at some practical examples. A tuple might be used to store coordinates, like coordinates equals 10, 20, where the order matters and the values should not change. A set could be used to store unique numbers, such as uniquenumbers equals 1, 2, 3, 3, which automatically becomes 1, 2, 3, because sets remove duplicates. A dictionary is perfect for storing structured data, like student equals name, Alice, age, 20, where each key provides a clear way to access specific information. These examples illustrate how each data structure solves different problems. By applying them appropriately, you can organize your data more effectively and write cleaner code. To wrap up, tuples, sets, and dictionaries are vital tools for data management in Python. Tuples ensure data integrity with immutability. Sets handle uniqueness and fast membership checks. And dictionaries provide efficient lookups with key value pairs. Understanding their characteristics will help you choose the right structure for any task. I encourage you to practice using these data structures in your own projects. The more you work with them, the more comfortable you'll become, and the better your Python programs will become. Thank you for your attention, and I hope this presentation has been helpful. Nested data structures are a powerful way to organize and manage complex information by combining lists, tuples, and dictionaries. These structures allow you to store multiple layers of data within a single container. For example, a list can hold other lists or dictionaries as its elements, enabling you to represent intricate relationships between data points. This approach is particularly useful in scenarios like matrices, where you need to store rows and columns of numbers, or in records, where each entry might have multiple attributes. By using nested structures, you can keep related data grouped together, making your code more intuitive and easier to manage. The flexibility of these structures allows you to adapt them to a wide range of problems, from storing user profiles to modeling real-world systems. There are several common types of nested structures in Python. A list of lists, for instance, might look like 1, 2, 3, 4, 5, where each element is itself a list. This is ideal for representing grids or tables of data. A list of dictionaries could be used to store multiple records, such as name, Alice, age, 30, name, Bob, where each dictionary represents a person with their details. Nested dictionaries, like students, Alice, 85, Bob, 90, allow you to store hierarchical data, such as student scores grouped under a class or subject. Tuples within lists, such as 1, 2, 3, 4, are useful when you need immutable pairs of values, like coordinates or fixed data points. Each of these structures has unique applications and can be combined in creative ways to model complex data scenarios. Accessing elements in nested data structures requires using multiple indices or keys, depending on the type of structure. For example, if you have a list of lists, you might use data 0, 1 to retrieve the second element of the first sublist. In a nested dictionary, you could access a value by chaining keys, such as data students Alice to get Alice's score. However, it's crucial to ensure that the indices or keys you're using actually exist, or your code may raise an error. To prevent this, you can use methods like get or check for the presence of keys before accessing them. Understanding how to navigate these structures is essential for working with real-world data, which often requires multiple steps to retrieve specific information. List comprehensions are a concise and efficient way to create lists in Python by transforming iterables. The basic syntax is expression for item in iterable if condition, which allows you to generate a new list by applying an expression to each item in an existing iterable. For example, x2 for x in range 5 would produce a list of squares from 0 to 4. This approach simplifies code by replacing traditional loops with a single line, making it easier to read and write. List comprehensions are particularly useful for performing simple transformations, such as filtering or modifying elements, and they can significantly reduce the amount of boilerplate code in your programs. However, they are best suited for straightforward operations, as overly complex comprehensions can become difficult to understand. Combining nested structures with list comprehensions can lead to more efficient and readable code. For instance, you can flatten a nested list by iterating through each sublist, and then each item within it as an item for sublist in data for item in sublist. This is helpful when you need to process all elements in a list of lists as a single sequence, filtering nested data, such as D for D in data if D age 25, allows you to extract only the entries that meet specific criteria, like selecting users over a certain age. Additionally, list comprehensions can be used to create nested structures, such as IDGE for J in range 3 for I in range 3, which generates a 3x3 multiplication table. By leveraging these techniques, you can handle complex data manipulation tasks with fewer lines of code and improved clarity. When working with nested data structures and list comprehensions, it's important to follow best practices to avoid common pitfalls. Overnesting can make your code harder to read and maintain, so it's wise to keep structures as flat as possible unless the hierarchy is necessary. List comprehensions are great for simple transformations, but for more complex logic, using traditional for loops may be clearer. Always validate the structure of your data before accessing elements to prevent errors, such as checking if a key exists in a dictionary or if an index is within bounds. Finally, remember that while list comprehensions can simplify code, they should not be used for tasks that require multiple steps or conditional branching, where a for loop might be more appropriate. In summary, nested data structures provide a flexible way to organize and represent complex data, making it easier to model real-world scenarios. List comprehensions offer a powerful tool for creating and manipulating lists efficiently, reducing the need for verbose loops. When combined, these concepts can enhance both the performance and readability of your code. To truly master these techniques, practice with real-world examples, such as processing user data, analyzing datasets, or building hierarchical models. By applying these principles in your projects, you'll develop a stronger understanding of how to handle intricate data structures and write cleaner, more effective Python code. Object-oriented programming is a way of organizing code by modeling real-world entities as objects. This approach focuses on creating reusable code, making it easier to manage and update. By using objects, we can break down complex problems into smaller, manageable parts. The core principles of object-oriented programming include classes, objects, inheritance, polymorphism, and encapsulation. These concepts work together to create structured and efficient code that is easy to maintain and scale. Understanding these elements is essential for mastering object-oriented programming in Python. A class is like a blueprint that defines the structure of an object. It outlines the properties and behaviors that an object of that class will have. For example, a class can contain variables to store data and functions to perform actions. When we create a class, we are essentially defining a new type of data that can be used to generate multiple instances. In Python, we use the keyword class followed by the name of the class to create one. This allows us to organize code in a way that reflects real-world relationships and interactions. An object is an instance of a class, meaning it is a specific realization of the blueprint defined by the class. Each object can have its own unique data while still following the structure defined by the class. For example, if we have a class called dog, we can create multiple dogs with different attributes like name and age. Objects interact with each other through methods, which are functions defined within the class. This allows us to create dynamic and flexible programs that can handle various scenarios. Attributes are the characteristics or data associated with an object, while methods are the actions that an object can perform. Attributes are typically variables that store information, such as a dog's name or age. Methods are functions that operate on the data within the class. For example, a dog class might have an attribute called name and a method called bark that prints a sound. These elements work together to define the behavior and state of an object, making it possible to create rich and interactive programs. Inheritance is a powerful feature that allows a class to inherit properties and methods from another class. This promotes code reuse and reduces redundancy. The class that is inherited from is called the base class or parent class, while the class that inherits is called the derived class or child class. For example, a poodle class can inherit from a dog class, gaining all its attributes and methods. This makes it easier to build complex systems by extending existing functionality, creating a hierarchical structure that mirrors real-world relationships. Polymorphism enables objects of different classes to be treated as objects of a common superclass. This means that a single method can behave differently depending on the object it is called on. For example, both a dog and a cat class can have a speak method, but each will produce a different sound. This flexibility allows for more generalized code that can handle various types of objects. Polymorphism is often achieved through method overriding, where a child class redefines a method from the parent class to suit its specific needs. Encapsulation is the practice of hiding the internal details of an object and exposing only what is necessary. This is done by restricting direct access to certain attributes and methods, often using private variables. In Python, variables can be made private by prefixing them with an underscore or double underscore. For example, a bank account class might have a private attribute for balance to prevent unauthorized modifications. This helps protect data integrity and ensures that objects are used in a controlled and predictable manner. Let's look at a practical example of object-oriented programming. We can create a car class with attributes like color and model, and methods like start and stop. When we create an object of this class, we can pass specific values for these attributes. For instance, my car equals car red. Tesla creates a red Tesla car. We can then call methods like mycar start to initiate the car's engine and mycar stop to turn it off. This demonstrates how classes and objects can be used to model real-world entities and their interactions. Conclusion: object-oriented programming is a fundamental concept in Python that helps create structured, scalable, and maintainable code. By understanding classes, objects, and their relationships, we can build complex systems that are easy to manage and extend. Practicing these concepts through real-world applications will deepen your understanding and improve your ability to solve programming problems. Embrace the principles of OOP to develop efficient and robust software solutions. Classes are the fundamental building blocks of object-oriented programming in Python. Think of a class as a blueprint that defines the structure and behavior of an object. When we create an object, it becomes an instance of that class, inheriting all the attributes and methods defined within it. Object-oriented programming, or OOP, is a programming paradigm that emphasizes reusability, modularity, and organization. By breaking down complex problems into smaller, manageable objects, we can write cleaner and more efficient code. The three core principles of OOP are encapsulation, which is about bundling data and methods together; inheritance, which allows a class to inherit properties from another class; and polymorphism, which enables objects of different classes to be treated as objects of a common superclass. These concepts work together to create flexible and scalable applications. To define a class in Python, we use the class keyword followed by the class name. For example, the code class dog. Pass creates an empty class called dog. While this might seem simple, classes can hold a variety of elements. They can have attributes, which are variables that store data, and methods, which are functions that define the behavior of the class. These attributes and methods are shared by all instances of the class. For example, if we add a species attribute to the dog class, all dog objects will have access to that attribute unless overridden. This structure allows us to create reusable code that can be extended and modified as needed. Once a class is defined, we can create objects by instantiating the class. This means using the class name followed by parentheses, like my dog equals dog. Each object created from a class is an independent instance, meaning it has its own set of attributes and methods. For example, if we assign my dog name equals Buddy, that value is specific to my dog and does not affect other dog objects. To access an object's attributes or methods, we use the dot operator. So if my dog has a method called bark, we can call it with my dog bark. This allows us to interact with each object individually, making it easier to manage and manipulate data. Class attributes are variables that are shared by all instances of a class. For example, if we define a species attribute inside the dog class, like species canine, every dog object will have access to this value. This is useful for storing data that is common to all instances, such as a default value or a constant. Methods, on the other hand, are functions defined within a class that operate on the class's data. For instance, a bark method could print woof. When called, these methods can be used to perform actions specific to the class, and they can access both class attributes and instance attributes. By combining attributes and methods, we can create rich, functional objects that encapsulate their behavior and data. The init method is a special function in Python that is automatically called when a new instance of a class is created. This method is used to initialize the object's attributes. For example, the dog class might have an init method that takes name and age as parameters and assigns them to the instance. This ensures that every dog object starts with the necessary data. The self parameter refers to the instance being created and is required in all method definitions. By using init, we can ensure that objects are properly initialized with the correct values, making the code more predictable and easier to manage. Inheritance is a powerful feature of OOP that allows a class to inherit properties and methods from another class. The class that is inherited from is called the parent or base class, while the class that inherits is called the child or derived class. For example, the animal class might have a speak method, and the cat class can inherit this method and override it to print meow instead. This allows for code reuse and creates a hierarchical structure that makes it easier to manage related classes. Inheritance also promotes a more organized code base, as changes to the parent class can automatically affect all child classes, reducing redundancy. Polymorphism refers to the ability of different classes to be treated as instances of a common superclass. This allows us to write functions that can work with objects of different types as long as they share a common interface. For example, a function called animalsuand could take any animal object and call its speak method. Whether the object is an animal or a cat, the function will execute the appropriate implementation. This flexibility makes it easier to write generic code that can handle various types of objects. Polymorphism also enables us to create more dynamic and extensible applications, as new classes can be added without modifying existing code. Encapsulation is the practice of hiding the internal state of an object and requiring all interaction to be done through methods. This is often achieved by using underscores to denote private attributes or methods, such as balance in a bank account class. While Python does not enforce strict access control, this convention signals to other developers that certain attributes should not be modified directly. Instead, we provide getter and setter methods to access or modify the data, ensuring that any changes are made in a controlled manner. Encapsulation helps prevent unintended modifications, improves code maintainability, and allows for better control over how data is accessed and updated. When working with classes and objects, there are several common mistakes to avoid. One of the most frequent is forgetting to include the self parameter in method definitions. This is essential because self refers to the instance of the class and is required for all methods. Another common error is mixing up class attributes and instance attributes. Class attributes are shared across all instances, while instance attributes are unique to each object. Overloading methods, which is not natively supported in Python, can lead to confusion. So it's better to use default parameters or separate methods for different functionalities. Lastly, failing to initialize attributes in the init method can result in runtime errors, as the object may lack unnecessary data. Being mindful of these pitfalls helps create more robust and reliable code. In summary, classes and objects form the foundation of object-oriented programming in Python. By understanding attributes, methods, inheritance, and encapsulation, we can build modular and reusable code. Practicing these concepts through real-world examples is essential for mastering OOP. Whether you're designing a simple application or a complex system, applying OOP principles can significantly improve the structure and efficiency of your code. As you continue learning, remember to experiment with different class designs and explore how these concepts can be applied to solve practical problems. With consistent practice, you'll become more confident in leveraging Python's powerful object-oriented features. Inheritance is a fundamental concept in object-oriented programming that allows a class to inherit properties and methods from another class. The class that is being inherited from is called the base class or parent class, while the class that inherits is known as the derived class or child class. This mechanism promotes code reuse and creates a hierarchical structure. For example, imagine a base class called vehicle, which contains common attributes like speed and fuel efficiency. From this, we can create derived classes such as car and bike, which inherit these properties, but also add their own unique features. The syntax for creating a derived class is straightforward. You define the derived class name followed by the base class in parentheses, like class derived base. This structure allows for a clear and organized way to build complex systems by leveraging existing code. The benefits of inheritance are numerous and significantly enhance the development process. First, code reusability is a major advantage. Instead of writing the same code multiple times, we can define it once in the base class and reuse it across multiple derived classes. This reduces redundancy and makes the code base more efficient. Second, inheritance enables hierarchical organization, making it easier to manage and understand relationships between classes. For instance, a hierarchy of shapes like circle, square, and triangle can all inherit from a common shape class. Third, scalability is improved because new classes can be added to the hierarchy without modifying existing code. Finally, maintainability is enhanced since changes in the base class automatically propagate to all derived classes, ensuring consistency and reducing the risk of errors. The super function plays a crucial role in inheritance by allowing a derived class to call methods from its base class. When a derived class is initialized, it often needs to set up attributes or perform actions defined in the base class. The super function facilitates this by invoking the base class's constructor. For example, if the base class vehicle has an init method that initializes attributes like make and model, the derived class car can use superinit to ensure these attributes are properly initialized. This ensures that the base class's setup is completed before the derived class adds its own functionality. Without super, the base class's methods might not execute, leading to incomplete object initialization and potential errors. Inheritance comes in several types, each serving different design scenarios. Single inheritance involves one base class and one derived class, creating a simple and direct relationship. For example, a dog class might inherit from a pet class. Multiple inheritance allows a derived class to inherit from multiple base classes, which can be useful for combining functionalities from different sources. However, this can also introduce complexity. Multi-level inheritance forms a chain, such as a being the base class for B, which in turn is the base for C. This is ideal for building layered hierarchies. Lastly, hierarchical inheritance occurs when multiple derived classes inherit from a single base class, such as vehicle being the parent of car, bike, and truck. Understanding these types helps in designing flexible and scalable class structures. Polymorphism is another cornerstone of object-oriented programming, allowing objects of different classes to be treated as objects of a common superclass. This means a single interface can represent multiple types, enhancing flexibility. For example, a shape class might have a method called draw, and derived classes like circle and square can override this method to provide their own implementation. This ability to use a common interface for different data types simplifies code and makes it more adaptable. Polymorphism also supports method overriding, where a derived class provides a specific implementation of a method already defined in the base class. This dynamic behavior allows programs to respond appropriately to different object types at runtime. Method overriding is a key aspect of polymorphism, enabling a derived class to provide a specific implementation of a method already defined in its base class. For instance, the vehicle class might have a move method that describes general movement, while the car class overrides this method to include details like engine speed or gear shifts. When an object of the car class calls move, the overridden method is executed, not the one from the vehicle class. This allows for more accurate and context-specific behavior. It's important to note that the method called depends on the actual object type, not the reference type, which is a core principle of dynamic method binding in object-oriented programming. Python employs a concept called duck typing, which determines an object's suitability based on its behavior rather than its class. This means that if an object has the required methods, it can be used in place of another object that is expected to have those methods. For example, both a bird and an airplane might have a fly method, so they can be treated interchangeably in code that calls fly. This approach eliminates the need for explicit type checks and allows for more flexible and dynamic code. Duck typing is a powerful feature of Python, as it encourages writing code that is adaptable and less reliant on rigid class hierarchies. Polymorphism extends beyond method, overriding to functions that can accept objects of different classes and call their methods dynamically. For instance, a function like drawShapeShape can work with circle, square, and triangle objects because they all implement a draw method. This flexibility allows functions to handle various types without needing to know their specific classes, reducing dependencies and increasing code reusability. By leveraging polymorphism, developers can write more generic and scalable code, as the same function can operate on different objects as long as they adhere to the required interface. This principle is widely used in frameworks and libraries to provide a consistent and adaptable API. In summary, inheritance and polymorphism are essential tools in Python for building maintainable, scalable, and flexible code. Inheritance allows for code reuse and hierarchical organization, reducing redundancy and improving manageability. Polymorphism enables dynamic method execution, allowing objects to behave in ways that are specific to their types, while maintaining a common interface. Together, these concepts enhance the structure of software systems, making them easier to extend and modify. Real-world applications include GUI frameworks, where widgets inherit from a base class, game development, where characters share common behaviors, and API design, where polymorphism allows for versatile and reusable components. By mastering these principles, developers can create robust and efficient Python programs. Exceptions are runtime errors that disrupt the normal flow of a program. These errors occur during the execution of code, not during the compilation phase. Common examples include dividing a number by 0, entering invalid data, such as a string where a number is expected, or trying to access a file that does not exist. Properly handling these exceptions ensures that programs remain stable and provide a better user experience. For instance, if a user inputs a non-numeric value when a number is required, the program can gracefully inform the user instead of crashing. Python provides a structured way to manage these errors using try-except blocks, which allow the program to catch and respond to exceptions without terminating abruptly. The syntax for handling exceptions in Python involves the try-except structure. The try block contains the code that may raise an exception, and the except block specifies the type of exception to catch. For example, if a program attempts to divide a number by 0, the code in the try block will trigger a 0 division error. The except block then executes to handle this specific error. Here is a simple example. In the try block, we attempt to divide 1 by 0. The except block catches the 0 division error and prints a message stating, "Cannot divide by 0." This mechanism prevents the program from crashing and allows it to continue running or provide feedback to the user. When dealing with multiple types of exceptions, it is essential to use multiple except blocks. Each except block can handle a different type of error, allowing the program to respond appropriately to various scenarios. For instance, if a program asks the user to input a number, it might encounter a value error if the input is not an integer, or a 0 division error if the user inputs 0. By structuring the code with separate except blocks for each error type, the program can provide specific messages for each situation. It is important to prioritize specific exceptions over general ones. For example, catching a value error before a general exception ensures that the program handles the most relevant error first. This approach enhances the clarity and reliability of the code. In addition to try-except blocks, Python offers the else and finally clauses to further structure exception handling. The else clause executes only if no exceptions occur in the try block, making it ideal for code that should run only when the program is functioning correctly. The finally clause, on the other hand, always executes regardless of whether an exception was raised. This is particularly useful for cleanup tasks, such as closing files or releasing resources. For example, a program that opens a file will use the finally clause to ensure the file is closed, even if an error occurs during file operations. The else clause can be used to confirm that the file was opened successfully, providing a clear flow of execution. Together, these clauses help create more robust and maintainable code. Custom exceptions allow developers to create their own error types, making the code more readable and specific to the problem at hand. In Python, this is achieved by defining a class that inherits from the built-in exception class. For example, a custom exception called invalid input error can be created to handle cases where user input does not meet certain criteria. The validated function demonstrates this by raising the invalid input error if the input age is negative. This approach not only improves code clarity, but also enables more precise error handling. By using custom exceptions, developers can better communicate the nature of errors to other parts of the program or to users, leading to more intuitive and maintainable code. Following best practices in exception handling ensures that code is both efficient and easy to maintain. One key principle is to catch specific exceptions rather than general ones. For example, instead of using a broad except block to catch all exceptions, it is better to handle specific error types like value error or zero division error. This prevents unintended behavior and makes the code more predictable. The else clause should be used for code that should only run if no exceptions occur, separating normal execution from error handling. The finally clause is essential for tasks like closing files or releasing resources, as it guarantees execution regardless of exceptions. Additionally, logging exceptions provides valuable information for debugging and helps users understand what went wrong. These practices contribute to more reliable and user-friendly programs. Exception handling is a critical aspect of writing robust and reliable Python programs. By using try-except blocks, developers can manage errors gracefully, preventing crashes and improving user experience. else, and finally clauses add structure to the code, ensuring that certain actions are taken under specific conditions. Custom exceptions allow for more precise and meaningful error messages, enhancing code readability and maintainability, adhering to best practices such as catching specific exceptions, using else, and finally clauses appropriately, and logging errors ensures that programs are both efficient and easy to debug. As you continue learning Python, practicing these concepts in real-world scenarios will help solidify your understanding and improve your ability to write resilient code. Welcome to the introduction to file handling in Python. File handling is a fundamental aspect of programming that allows you to interact with files stored on your computer. Whether you need to read data from a file, write new information, or modify existing content, Python provides tools to perform these tasks seamlessly. Common operations include opening a file, reading its contents, writing new data, and closing the file to free up system resources. Files can be of different types, such as text files, which contain human-readable characters, or binary files, which store data in a format that machines can process directly. Examples of binary files include images, videos, and executable programs. Understanding file handling is essential for tasks like data analysis, logging, and configuration management. To begin working with files in Python, you use the open function. The syntax for opening a file is straightforward. File equals open filename, mode. The first argument is the name of the file you want to access, and the second argument specifies the mode in which you want to open it. The most common modes are R for reading, W for writing, and A for appending. The R mode is the default if no mode is specified, but it requires the file to exist. If you attempt to open a file in R mode that does not exist, Python will raise an error. The W mode creates a new file or overwrites an existing one, making it ideal for writing new content. The A mode allows you to add content to the end of a file without erasing its existing data. Lastly, the R+ mode enables both reading and writing, but the file must already exist. Choosing the correct mode is crucial to avoid unintended data loss or errors. Once a file is open, you can read its contents using several methods. The file read method reads the entire content of the file as a single string, which is useful for small files. For larger files, the file readline method is more efficient, as it reads one line at a time, allowing you to process data incrementally. If you need to work with all lines simultaneously, the file Read Lines method returns a list of strings where each element represents a line in the file. It is important to remember that after reading, you must close the file using the file close method. Failing to do so can lead to resource leaks, where the file remains locked by the program, preventing other processes from accessing it. Closing the file ensures that all changes are saved and system resources are properly released. Writing to a file in Python is equally straightforward. The file write text method allows you to add a single string to the end of a file. For multiple lines, the file WriteLinesList method is useful as it takes an iterable of strings, such as a list, and writes each element to the file. When writing, the mode you choose determines how the content is handled. In W mode, the file is either created or overwritten, meaning any existing content is erased. This is ideal for scenarios where you want to replace the entire file with new data. In contrast, a mode appends the new content to the end of the file, preserving the existing data. Understanding the difference between overwriting and appending is critical for tasks like logging, where you want to add new entries without losing previous records. Python offers a variety of file modes to suit different needs. The R mode is for reading only, ensuring that you cannot modify the file's contents. The W mode allows writing, but creates a new file or overwrites an existing one. The A mode is for appending, adding data to the end of the file without altering existing content. The R+ mode enables both reading and writing, but the file must already exist. This is useful for modifying specific parts of a file. The W+ mode creates a new file or overwrites an existing one, allowing both reading and writing. This is ideal for scenarios where you need to generate a new file and then read from it. Finally, the A+ mode allows appending and reading, making it suitable for adding new data while also accessing the file's contents. Each mode has its own use case, and selecting the right one ensures your program behaves as intended. To ensure your file operations are robust and efficient, follow these best practices. One of the most important is to use the with statement, which automatically closes the file once you exit the block. This eliminates the risk of forgetting to close the file manually. For example, with open file txt, R as file, content equals file read ensures the file is properly closed after reading. Always check if a file exists before attempting to read it, though handling exceptions like file not found error is often more reliable than checking explicitly. When working with files, unexpected errors can occur, so using try except blocks helps manage these issues gracefully. If you do not use the with statement, remember to close the file explicitly with file close. These practices prevent data corruption, resource leaks, and other common pitfalls. In conclusion, file handling is a critical skill for any Python programmer. It enables you to store, retrieve, and manipulate data efficiently, making it indispensable for tasks like data processing, logging, and configuration management. Understanding the different file modes, reading and writing methods, and best practices ensures that your programs handle files correctly and safely. By practicing with the open function, read and write methods, and the with statement, you will develop the ability to work with files confidently. Whether you are building a simple script or a complex application, mastering file handling will enhance your ability to manage data effectively. Keep experimenting with different scenarios to solidify your understanding. Good morning, everyone. Today, we will explore two essential data formats used in Python programming, CSV and JSON. CSV, or comma-separated values, is a straightforward method for storing tabular data like spreadsheets or database tables. Each line in a CSV file represents a row, and values are separated by commas. This simplicity makes it ideal for basic data exchange. On the other hand, JSON, which stands for JavaScript Object Notation, is a lightweight and versatile format for structured data. It uses key-value pairs and supports nested structures, making it perfect for complex data. Both formats are widely used in software development for transferring data between systems, such as from a server to a web application. Python provides built-in libraries like the CSV module for CSV tasks and the JSON module for JSON operations, making these formats easy to work with. Now, let's discuss how to read CSV files in Python. The CSV module is the go-to tool for this. The CSV reader function allows you to read a CSV file line by line, treating each row as a list of values. For example, if your file has headers like name and age, the first row might be John, 30. However, if you want to access data using column names, the CSV dict reader is more convenient. This function reads each row as a dictionary, where the keys are the column headers. So the same row would become name, John, age 30, making it easier to reference data by name. Here's a simple example. Open the file, create a reader object, and iterate through the rows. This approach is essential for processing data from spreadsheets or databases. Next, we'll look at writing CSV files. The CSV writer function is used to create a CSV file and write rows of data. You can use the writer-write-row method to add individual rows, which is useful for generating reports or exporting data. For instance, writing name, age as the first row creates a header. If your data is structured as dictionaries, the CSV dict writer is the right choice. This function allows you to write rows based on dictionary keys, ensuring that the data aligns with the correct columns. For example, a dictionary like name, Alice, age 25 would be written as a row in the CSV file. This method is particularly helpful when working with data that has named fields, such as user profiles or product listings. Moving on to reading JSON files, the JSON module in Python is the primary tool. The JSON load function reads a JSON file and converts it into a Python object, such as a dictionary or list. This is incredibly useful for parsing data from configuration files or API responses. If you have a JSON string instead of a file, the JSON loads function does the same job, converting the string into a Python structure. For example, a JSON string like name, John, age 30, becomes a dictionary with keys name and age. This flexibility allows you to work with JSON data, whether it's stored in a file or transmitted over a network. Understanding these functions is crucial for handling data in modern web applications. Now, let's discuss writing JSON files. The JSON dump function writes a Python object to a file in JSON format, making it easy to save data for later use. For instance, if you have a dictionary containing user data, you can use JSON dump to serialize it into a JSON file. The JSON dumps function, on the other hand, converts a Python object into a JSON string, which is useful for sending data over a network or storing it in a text file. When writing JSON, it's important to use the indent parameter to format the output neatly, such as indent 4 spaces for readability. However, not all Python objects can be be serialized. Only those with basic data types like lists, dictionaries, strings, and numbers. This ensures compatibility when exchanging data between systems. Let's compare CSV and JSON to understand their strengths and weaknesses. CSV is best suited for flat, tabular data, such as spreadsheets or database exports. Its simplicity makes it easy to read and write, but it lacks support for hierarchical or nested structures. JSON, on the other hand, is more flexible, allowing for complex, nested data. For example, a JSON object can contain arrays of objects, making it ideal for representing relationships between data points. While CSV is easier for basic tasks, JSON is more human-readable and widely used in APIs and modern web services. Choosing between them depends on your data's complexity and the system you're working with. Both CSV and JSON have specific use cases that make them indispensable. CSV is commonly used for exporting data from spreadsheets or importing it into databases. For instance, a business might export sales data to a CSV file and then import it into a database for analysis. JSON is often used in configuration files, where key value pairs define settings for an application. It's also the standard for API responses, allowing web services to send structured data to clients. In data analysis, CSV is great for quick data exploration, while JSON is preferred for handling nested data from external sources. These formats are also vital in automation tasks, such as generating reports or integrating different systems. To ensure smooth data handling, follow these best practices. Always validate data before reading or writing to avoid errors. For example, check if a file exists or if the data conforms to expected formats. Use exception handling like try except blocks to catch and manage errors such as missing files or invalid data. In CSV, maintain consistent delimiters like commas or tabs to prevent parsing issues. For JSON, ensure proper indentation and encoding to avoid syntax errors. These practices help create robust applications that handle data reliably, even when unexpected issues arise. When troubleshooting data issues, start by checking file paths and permissions. A common problem is a file not being found, which can be resolved by verifying the path ensuring the program has access. Use try-except blocks to handle errors gracefully, providing meaningful messages for users. For JSON, validate the syntax using online tools to catch issues like missing commas or brackets. In CSV, ensure that there are no extra or missing commas, which can disrupt the structure of the data. These steps help identify and resolve problems quickly, keeping your data workflows running smoothly. In conclusion, mastering CSV and JSON is essential for any Python programmer. These formats are fundamental for data handling in various applications, from simple data exports to complex API integrations. By practicing reading and writing both formats, you'll enhance your ability to work with real-world data. Don't stop at the basics. Explore advanced features like nested JSON structures or CSV dialects to tackle more complex scenarios. As you continue learning, these skills will become invaluable in your journey to become a proficient Python developer. A module is a Python file that contains functions, classes, and variables. Think of it as a container that holds related code to make it easier to manage. By using modules, you can break down large programs into smaller, more manageable pieces. This not only helps in organizing your code, but also makes it reusable across different projects. For example, the math module provides mathematical functions, and the random module offers functions for generating random numbers. These are built-in modules, meaning they come with Python and are ready to use without any additional installation. When you import a module, you gain access to its functions and variables, allowing you to leverage existing code instead of writing everything from scratch. Using modules is essential for writing clean and efficient code. One of the main benefits is that modules improve readability. When your code is divided into logical sections, it becomes easier to understand and navigate. Modules also enhance maintainability. If you need to update or fix a part of your code, you can focus on the specific module without disrupting the entire program. Another advantage is that modules prevent code duplication. Instead of rewriting the same code in multiple places, you can import a module and use its functionality wherever needed. This is especially useful in team environments where collaboration becomes smoother when code is organized into distinct modules. Additionally, modules make debugging and testing more straightforward because because you can isolate issues to specific sections of your code. A package is a directory that contains multiple modules, allowing you to organize related code in a hierarchical structure. To mark a directory as a package, you need to include a special file called init py. This file can be empty or contain initialization code that runs when the package is imported. Packages are particularly useful for large projects where you need to group modules by functionality. For instance, the NumPy package provides tools for numerical computing, while the requests package simplifies HTTP requests. By using packages, you can create a clear structure for your code, making it easier to locate and manage modules. This hierarchical organization also helps avoid naming conflicts and ensures that your code remains scalable as it grows. Importing modules and packages is a fundamental part of Python programming. The import statement allows you to load a module or package into your current script. For example, importing the math module gives you access to all its functions, such as math, sqrt for calculating square roots. Alternatively, you can import specific functions from a module using the from import syntax. For instance, from math import sqrt lets you call sqrt directly without the math prefix. Once imported, you use the dot notation to access functions or classes within the module, like math sqrt25. For third-party packages, you need to install them first using pip, the Python package installer. This process ensures that you can access a vast ecosystem of pre-built tools and libraries to enhance your projects. Python has two types of modules: standard and third-party. Standard modules are included with Python by default, so you don't need to install anything to use them. Examples include OS for interacting with the operating system, sys for system-specific functions, and data time for handling date and time operations. These modules are reliable and well documented, making them a great starting point for most projects. Third-party modules, on the other hand, are developed by the community and must be installed using pip. Popular examples include NumPy for numerical computations, Flask for web development, and Pandas for data analysis. While third-party modules offer powerful features, it's important to check their compatibility with your Python version and ensure they are secure, especially when using them in production environments. Creating a custom module is a simple yet powerful way to organize your code. To start, you can create a Python file, such as calculator py, and define functions or classes within it. For example, you might write an add function that takes two numbers and returns their sum. Once the module is created, you can import it into another script using the import statement. This allows you to reuse your code across multiple projects. For instance, if you have a function called add in calculator py, you can call it as calculator add 2, 3 to get the result 5. Custom modules not only help in keeping your code organized, but also make it easier to share and collaborate with others. By encapsulating related functions into a single module, you reduce complexity and improve the overall structure of your programs. Creating a custom package involves structuring your code into a directory with multiple modules. Begin by creating a folder, such as My Package, and place your modules inside it. For example, you might have a module called mathutils py that contains functions like multiply. To designate the folder as a package, add an init py file, which can be empty or include initialization code. This file tells Python that the directory should be treated as a package. Once set up, you can import modules from the package using the dot notation. For example, from My Package, mathutils import multiply allows you to call the multiply function directly. Packages are ideal for organizing large projects, as they provide a clear hierarchy and make it easier to manage complex code bases. This structure also helps in avoiding naming conflicts and ensures that your code remains modular and scalable. In summary, modules and packages are essential tools for organizing and reusing Python code. They allow you to break down complex programs into manageable components, improving readability, maintainability, and collaboration. By importing built-in or third-party modules, you can leverage existing functionality without reinventing the wheel. Custom modules and packages enable you to structure your projects in a way that is both scalable and efficient. As you practice importing and creating modules, you'll find that your coding workflow becomes more streamlined and productive. Whether you're working on a small script or a large application, mastering modules and packages will significantly enhance your ability to write clean, reusable, and maintainable code. The Python Standard Library is a vast collection of built-in modules and functions designed to simplify common programming tasks. This library acts as a toolkit that comes with Python, allowing developers to avoid reinventing the wheel for everyday operations. For instance, instead of writing code from scratch to handle file operations, you can use modules like OS or Shuttle. The standard library also includes functions for mathematical computations, system interactions, and data manipulation, making it an essential resource for any Python programmer. By leveraging these pre-written components, you can significantly reduce development time and focus on solving more complex problems. Whether you need to read a file, calculate a square root, or manage system paths, the standard library has you covered. Several key modules in the standard library are widely used across Python applications. The math module provides essential mathematical functions such as square roots, trigonometric calculations, and constants like pi. The OS module allows interaction with the operating system, enabling tasks like navigating file directories, renaming files, or creating new folders. The sys module offers access to system-specific parameters and functions, such as command line arguments and program exit control. The data time module handles date and time operations, which are critical for logging, scheduling, and time-based calculations. Lastly, the random module generates random numbers and shuffles data, making it valuable for simulations, games, and security-related tasks. These modules form the backbone of many Python programs and are worth mastering. The math module contains a variety of functions for mathematical operations. For example, the sqrt function calculates the square root of a number, which is useful in geometry and physics problems. The sin function returns the sine of an angle measured in radians, a common requirement in scientific computing. The pi constant represents the mathematical value of pi, approximately 3.14159, and is essential for calculations involving circles or trigonometry. Additionally, the log function computes the natural logarithm of a number, which is vital in fields like engineering and data analysis. These functions are optimized for performance and accuracy, ensuring reliable results for a wide range of applications. The OS module provides functions for interacting with the operating system. The getCould function retrieves the current working directory, which is helpful for determining where a script is running. The listdir function lists all files and directories within a specified path, making it easy to navigate the file system. The rename function allows you to change the name of a file or directory, which is useful for organizing data. Finally, the makeDirs function creates a directory and any necessary parent directories, ensuring that your file structure is properly set up. These tools are indispensable for tasks that involve file management and system operations. The SIS module offers functions for accessing system-specific parameters and functionalities. The argv list contains command line arguments passed to a script, enabling users to customize program behavior at runtime. The exit function terminates the program, which is useful for handling errors or user requests. The path list specifies the directory's Python searches for modules, which is critical for managing dependencies. Lastly, the version attribute displays the Python version being used, which helps in ensuring compatibility with different environments. These features make the SIS module a powerful tool for system-level programming and script control. The DataTime module provides tools for working with dates and times. The Now function retrieves the current date and time, which is useful for logging events or tracking timestamps. The Today function returns the current date, making it easy to perform date-based calculations. The TimeDelta class represents a duration, allowing you to add or subtract time intervals from a date. The SDRFTime function formats date and time objects into human-readable strings, which is essential for displaying information in a user-friendly way. These capabilities make the DataTime module a cornerstone of applications that require time-sensitive operations. The Random module offers functions for generating random numbers and selecting random elements. The Randint function returns a random integer within a specified range, which is useful for games or simulations. The Choice function selects a random element from a sequence, such as a list or tuple, which can be used for tasks like picking a random item from a dataset. The Shuffle function rearranges the elements of a sequence in place, making it ideal for applications like card games or randomized data processing. Lastly, the Random function generates a random floating point number between 0 and 1, which is often used in probability calculations or randomization algorithms. The JSON module is used for data serialization, allowing Python objects to be converted into JSON format and vice versa. The Dumps function transforms a Python object into a JSON string, which is useful for sending data over a network or storing it in a file. The loads function parses a JSON string into a Python object, enabling data to be read and manipulated. The dump function writes a Python object directly to a JSON file, while the load function reads a JSON file into a Python object. These functions are essential for applications that require data exchange between different systems or platforms, such as web services or configuration files. Practical use cases for the standard library include dynamically handling file paths with the OS module, which ensures scripts work across different environments. The data time module is often used to log timestamps in applications, providing a record of when events occur. The random module can generate secure tokens for authentication or shuffle data for machine learning tasks. Combining modules like OS and JSON allows you to read and write JSON files efficiently, such as loading configuration settings from a file. These examples demonstrate how the standard library simplifies complex tasks and enhances the functionality of Python programs. The Python standard library significantly enhances the language's capabilities by providing ready-to-use modules for a wide range of tasks. Mastering these modules improves efficiency, reduces code complexity, and allows developers to focus on solving higher-level problems. Beyond the modules mentioned, there are many others like Ray for regular expressions or collections for advanced data structures. Exploring these tools and practicing their integration into real-world projects is key to becoming proficient in Python. By leveraging the standard library, you can build robust, maintainable, and scalable applications with ease. Regular expressions, often referred to as regex, are powerful tools used to match, search, or manipulate text based on specific patterns. They are essential in programming for tasks like validating user input, extracting information from large datasets, or modifying text in a structured way. For example, if you need to check if a string is a valid email address or extract all dates from a document, regular expressions can handle these tasks efficiently. In Python, the Ray module provides a set of functions and methods that allow developers to work with regex. This module is a cornerstone for text processing, enabling everything from simple string searches to complex pattern substitutions. Whether you're cleaning data, parsing logs, or validating forms, understanding regex can significantly streamline your workflow. To use regular expressions effectively, it's important to understand their basic syntax and meta-characters. Literals are straightforward. They match exact characters, such as the letter or the number 1. However, meta-characters add flexibility by representing special patterns. For instance, the dot character matches any single character except a new line. The asterisk indicates 0 or more of the preceding element, while the plus sign denotes 1 or more. The question mark allows for 0 or 1 occurrence. Brackets, like a Z, define character classes, enabling matches for a range of characters. Other meta-characters, such as the caret and dollar sign, anchor patterns to the start and end of a string, respectively. Additionally, shorthand notations like \D for digits and \W for word characters simplify complex patterns. Mastering these elements allows you to construct precise and efficient regex expressions. Regular expressions are widely used for common tasks like validating email addresses, parsing phone numbers, and identifying dates. For emails, a typical pattern might start with a username that includes letters, numbers, and certain symbols like dots, underscores, percent signs, plus signs, or hyphens, followed by an @ symbol and a domain. This ensures that the email adheres to standard formatting rules. Phone number patterns often include optional country codes, separators like hyphens or spaces, and specific digit groupings. For example, a regex might allow for a plus sign at the beginning, followed by up to 3 digits, then 3 digits, and finally 4 digits, with optional spaces or dots in between. Dates in the format YYYYMMDD can be matched using a pattern that requires 4 digits for the year, 2 for the month, and 2 for the day, separated by hyphens. These examples illustrate how regex can handle real-world data with varying formats. In Python, the array module is the primary tool for working with regular expressions. To use it, you first import the module with the command import array. The module offers several functions, each serving a specific purpose. The match function checks if a pattern matches the beginning of a string, while search scans the entire string for a match. Find all returns all non-overlapping matches as a list, making it ideal for extracting multiple instances. Sub replaces occurrences of a pattern with a specified string, and split split divides a string based on a regex pattern. For efficiency, especially when reusing patterns, you can compile them using recompile, which creates a regex object that can be applied multiple times. Understanding these functions and how to use them effectively is crucial for leveraging regex in Python. The Ray module includes several key functions for working with regex patterns. The match function is used to check if a pattern matches the start of a string. For example, if you're validating a password that must start with a letter, match ensures the first character meets the criteria. The search function, on the other hand, scans the entire string for a match, making it suitable for tasks like finding a keyword in a document. Find all is particularly useful for retrieving all instances of a pattern, such as extracting all email addresses from a text. Each function has its unique use case, and choosing the right one depends on whether you need to check the start of a string, search the entire text, or collect all matches. These tools collectively provide a robust set of options for text processing. Grouping and capturing in regular expressions allow you to isolate specific parts of a pattern for further use. By enclosing parts of a regex in parentheses, you create groups that can be accessed individually. For example, a pattern like \d4 \d2 \d2 captures the year, month, and day from a date string. The group method, such as group 1, retrieves the first captured group, while group 2 gets the second. This is particularly useful when you need to extract structured data from a larger string. Additionally, non-capturing groups, denoted by, allow you to group elements without storing the matched text, which can improve performance. These features make it easier to handle complex patterns and retrieve specific information from matches. Advanced regex features like lookaheads and backreferences extend the capabilities of regular expressions. Lookaheads, such as equals, assert that a certain pattern follows the current position without consuming characters. For instance, A equals B matches the letter only if it is followed by B backreferences, like \1 or \2, refer to previously captured groups, enabling you to match repeated patterns. For example, a regex like \w plus \s plus \1 would find repeated words. Non-capturing groups using help organize patterns without storing the matched text, which is useful for efficiency. These advanced techniques allow for more precise and dynamic pattern matching, making regex even more powerful for complex text processing tasks. Regular expressions have numerous practical applications in data processing and analysis. They are commonly used to extract information from unstructured data, such as parsing log files to identify error messages, or scraping web content for specific details. Validation is another critical use case, ensuring that user inputs like passwords, emails, or phone numbers meet certain criteria. For example, a regex can enforce password strength by requiring a mix of uppercase letters, lowercase letters, and numbers. Text substitution is also widespread, such as replacing URLs with placeholders in a document or anonymizing sensitive data. These applications highlight the versatility of regex in solving real-world problems efficiently and effectively. Regular expressions are a powerful tool for text processing in Python, offering a flexible way to search, match, and manipulate strings. Mastering their syntax and functions enables developers to handle tasks that would otherwise require complex code. Whether you're validating input, extracting data, or transforming text, regex can streamline your workflow and reduce development time. However, like any skill, proficiency with regex comes with practice. Engaging with real-world examples, such as processing log files or validating user data, helps reinforce understanding and improve problem-solving abilities. By continuing to explore and experiment with regex, you can unlock its full potential and become more efficient in your Python programming endeavors. Today, we will delve into advanced string operations, which go beyond the basic functions you may already be familiar with. These techniques are essential for handling complex text processing tasks. Whether you're working with user input, data cleaning, or generating dynamic output. By mastering these skills, you will not only improve the efficiency of your code, but also make it more readable and easier to maintain. We will explore various methods and formatting strategies that will empower you to manipulate strings with greater precision and flexibility. This knowledge will be particularly valuable when dealing with large datasets or when you need to present information in a structured and consistent manner. String formatting is a powerful tool that allows you to create dynamic and readable output. One of the most modern approaches is using f-strings, which which let you embed expressions directly within string literals. This makes your code more intuitive and easier to debug. Another technique is the format method, which provides a way to structure strings by replacing placeholders with values. This is especially useful when you need to maintain a specific layout or when working with multiple variables. Additionally, format specifiers enable you to control how numbers, dates, and other data types are displayed. For example, you can specify the number of decimal places for a floating point value or format a date in a particular style. These techniques are crucial for generating clean and professional-looking output in applications ranging from reports to user interfaces. String manipulation methods are fundamental for tasks like splitting text into parts, modifying content, or cleaning up data. The split method allows you to break a string into a list of substrings based on a specified delimiter, which is useful for parsing log files or CSV data. The join method does the opposite, combining elements of a list into a single string, making it ideal for constructing sentences or URLs. The replace method helps substitute specific patterns or characters within a string, which is handy for correcting typos or transforming data. Meanwhile, the strip, lstrip, and rstrip methods remove unwanted white space from the beginning, end, or both ends of a string. These methods are often used in data preprocessing to ensure consistency and accuracy in text analysis. Advanced formatting options give you greater control over how your strings are displayed. For instance, you can use alignment specifiers like less than, greater than, or caret to left align, right align, or center text within a given width. This is particularly useful when generating tables or reports where visual alignment matters. Padding with characters such as zeros or asterisks can also enhance readability, especially when formatting numbers or creating visual separators. Additionally, precision specifiers allow you to define the number of decimal places for floating point numbers, ensuring that numerical data is presented clearly and consistently. These features are invaluable when dealing with financial data, scientific calculations, or any scenario where exact formatting is required. Combining string methods can unlock more complex transformations, enabling you to handle multi-step tasks efficiently. For example, splitting a string and then joining the parts with a different delimiter can restructure data in a meaningful way. The find and index methods are useful for locating substrings within a larger string, which is essential for tasks like searching for keywords or parsing structured text. Meanwhile, validation methods like isAlpha and isDigit help verify whether a string contains only alphabetic characters or numeric values, respectively. These techniques are critical for input validation, ensuring that user-provided data meets specific criteria before further processing. By leveraging these methods together, you can create robust and reliable text handling workflows. Let's explore practical examples and best practices to apply these techniques effectively. When formatting user input, such as dates or currencies, consistency is key. For instance, you can use formatting to ensure all dates are displayed in the same pattern, improving readability. Avoiding string concatenation in loops is another important consideration, as it can lead to performance issues with large datasets. Instead, using methods like f-strings or the format method is more efficient and cleaner. F-strings, in particular, are recommended for their clarity and modern syntax, making your code easier to understand and maintain. These practices not only enhance performance, but also contribute to a more professional and scalable code base. In summary, mastering advanced string operations is a crucial step in becoming a proficient Python developer. These techniques not only improve the efficiency of your code, but also make it more readable and adaptable to various tasks. Whether you are formatting data for presentation or manipulating text for analysis, the skills covered today will serve you well in real-world scenarios. To solidify your understanding, I encourage you to practice these concepts with different datasets and applications. The more you experiment, the more confident you will become in handling complex string operations, ultimately making you a more versatile and effective programmer. The DataTime module in Python is a powerful tool for working with dates and times. It includes several classes such as DataTime, date, time, and time delta. The DataTime class allows you to handle both date and time information together, while the date class focuses solely on calendar dates. The time class is used for time-only values, and the time delta class helps calculate differences between dates and times. These classes are essential for a wide range of applications, from logging events in software to scheduling tasks and analyzing time-based data in fields like finance or scientific research. Whether you need to track when a user logged in or calculate how long a process took, the data time module provides the necessary tools to handle these tasks efficiently. To create a data time object in Python, you can use the data time class and pass in the year, month, day, hour, minute, and second as parameters. For example, data time 2023 10 5 14 30 would create a specific date and time. If you only need the current date, the date today method is useful. This returns the current date without any time component. Similarly, the time method can be used to create objects that represent time values alone. These functions are particularly helpful when you need to capture the current time or work with specific date and time values in your code. Understanding how to construct these objects is the first step in manipulating date and time data effectively. Parsing and formatting dates is a common task when working with data from external sources. The strTime method allows you to convert a string into a data time object by specifying the format of the string. For instance, using 2020-31005 with the format %y%m%d would parse the string into a data time object. On the other hand, the strFtime method does the opposite, converting a data time object into a string based on a specified format. This is useful for displaying dates in a user-friendly way, such as generating log entries with timestamps. By mastering these methods, you can handle date and time data in various formats and ensure consistency across different systems or user inputs. When working with time zones, it is important to account for differences in local times across the globe. Python provides the PITS library, or the time zone class, in the data time module to create time zone aware data time objects. For example, you can use PITS time zone UTC to get the current time in coordinated universal time. This is crucial for applications that operate in multiple regions, ensuring accurate time calculations. Additionally, the time delta class is used to calculate the difference between two data time objects. For instance, subtracting one date from another gives you the number of days, hours, or minutes between them. These tools help manage time zone complexities and perform precise, time-based computations. The data time module has many practical applications in real-world scenarios. One common use is calculating the number of days between two dates, which can help in project planning or tracking deadlines. Formatting timestamps is another key task, as it allows you to present dates and times in a consistent and readable format for users or logs. Scheduling tasks based on specific time intervals, such as running a script every day at a certain hour, is also made easier with data time. Furthermore, handling user input with varying date formats requires parsing and converting data into a standardized format. These examples demonstrate how the data time module can be applied to solve a wide range of problems in software development and data processing. In conclusion, the data time module is a versatile and essential part of Python programming for managing dates and times. By understanding how to create, parse, and format data time objects, as well as handle time zones and calculate time differences, you can tackle complex tasks with confidence. The ability to work with date and time data is critical in many fields, from web development to data analysis. Practicing with real-world examples will help reinforce these concepts and improve your ability to handle time-based data effectively. As you continue to explore Python, the data time module will remain a valuable tool in your programming arsenal. Python libraries are essential tools that significantly enhance the capabilities of the core Python language. While Python itself is a versatile programming language, its true power lies in the vast ecosystem of libraries that extend its functionality. These libraries provide pre-written code that can handle complex tasks, allowing developers to focus on solving problems rather than reinventing the wheel. For instance, libraries like NumPy and Pandas are specifically designed to simplify data manipulation and analysis. NumPy excels at numerical computations with its efficient handling of arrays, while Pandas offers powerful data structures for organizing and analyzing structured data. By leveraging these libraries, developers can reduce the time required to write code and improve the efficiency of their programs, making them indispensable in fields like data science, machine learning, and scientific research. NumPy, short for numerical Python, is a foundational library for numerical computing in Python. It is designed to handle large, multi-dimensional arrays and matrices, which are central to many scientific and mathematical operations. Unlike standard Python lists, NumPy arrays are optimized for performance, enabling faster and more efficient computations. This library provides a wide range of mathematical functions that can operate on these arrays, such as linear algebra operations, Fourier transforms, and statistical calculations. Because of its efficiency and versatility, NumPy serves as the backbone for many other scientific computing libraries, including SciPy, scikit-learn, and TensorFlow. Its ability to handle complex numerical tasks makes it a critical tool for researchers, engineers, and data scientists working with large datasets. The key features of NumPy make it a powerful tool for numerical computing. One of its most notable attributes is the high-performance n-dimensional array object, which allows for efficient storage and manipulation of data. This array structure supports broadcasting, a feature that enables arithmetic operations on arrays of different shapes and sizes, eliminating the need for explicit loops. Additionally, NumPy integrates seamlessly with C, C++, and Fortran code, allowing developers to leverage existing high-performance code for computationally intensive tasks. The library also includes built-in support for advanced mathematical operations, such as linear algebra, Fourier transforms, and random number generation, making it suitable for a wide range of applications, from physics simulations to machine learning algorithms. Pandas is a library that revolutionizes data manipulation and analysis by providing intuitive data structures like data frames and series. These structures are designed to handle structured data, such as data stored in CSV files, Excel spreadsheets, or SQL databases. A data frame resembles a spreadsheet with rows and columns that can be easily filtered, sorted, and transformed. Similarly, a series is a one-dimensional array that can hold data of various types. Pandas simplifies tasks like cleaning data, handling missing values, and performing aggregations, making it an essential tool for data preprocessing. Its ability to efficiently manage and analyze structured data makes it a go-to library for data scientists and analysts working with real-world datasets. Pandas offers several features that enhance its flexibility and usability. One of its strengths is flexible data alignment, which automatically adjusts data based on labels, ensuring that operations are performed on the correct elements. It also excels at handling missing data, providing tools to detect, replace, or remove null values, which are common in real-world datasets. The library supports reshaping and pivoting of data, allowing users to restructure their data for different analysis needs. Additionally, Pandas includes robust time series functionality, making it ideal for analyzing data that changes over time, such as stock prices or weather data. Its integration with NumPy and other libraries further enhances its capabilities, enabling seamless workflows between different data processing stages. To illustrate the practical applications of these libraries, let's consider a few examples. With NumPy, you can create multi-dimensional arrays and perform mathematical operations on them. For instance, you might generate a 2D array representing a dataset and compute the sum of its elements, or apply a mathematical function to each value. In Pandas, you can load a CSV file into a data frame and perform operations like filtering rows based on specific criteria, aggregating data to calculate statistics, or merging datasets. When combined, NumPy and Pandas can form powerful data processing pipelines. For example, you might use NumPy to perform numerical calculations on a dataset, and then use Pandas to organize and visualize the results. These examples demonstrate how these libraries can streamline complex tasks and improve productivity in data analysis workflows. The applications of NumPy and Pandas span across various industries and domains. NumPy is widely used in scientific research for tasks like simulations, data analysis, and machine learning, where numerical computations are essential. It is also a key component in engineering simulations, where large datasets need to be processed efficiently. On the other hand, Pandas is indispensable in financial data analysis, where it helps in tracking stock prices, managing portfolios, or identifying trends. Businesses rely on Pandas for business intelligence tasks, such as generating reports or analyzing customer data. Both libraries are critical in data science workflows, where they enable data processing, transformation, and analysis. Their widespread adoption in industries underscores their importance in driving data-driven decision-making and innovation. In conclusion, NumPy and Pandas are indispensable tools for anyone working with data in Python. NumPy provides the foundation for efficient numerical computations, making it ideal for tasks that require high performance and mathematical precision. Pandas, with its intuitive data structures and powerful data manipulation capabilities, simplifies the process of working with structured data. Together, these libraries form the backbone of data science and analysis, enabling professionals to handle complex tasks with ease. By mastering these tools, Python programmers can significantly enhance their ability to process, analyze, and derive insights from data, making them invaluable assets in both academic and industrial settings. Pandas is a powerful Python library designed for data manipulation and analysis. It provides essential tools that make working with structured data significantly easier. The two primary data structures in Pandas are series and data frame. A series is like a one-dimensional array that can hold any data type, and it is labeled, which means each element has a unique identifier. A data frame is a two-dimensional table with rows and columns, similar to a spreadsheet or SQL table. These structures allow users to handle complex data operations efficiently. Pandas is widely used in industries for tasks such as cleaning, transforming, and analyzing data. It is also fundamental for data scientists and analysts to perform statistical analysis and create visualizations. Whether you are dealing with small data sets or large-scale data, Pandas offers the flexibility and functionality to handle a wide range of data challenges. To use Pandas, you first need to install it. If it is not already installed on your system, you can install it using the pip package manager by running the command pip install pandas. Once installed, you can import the library into your Python code with the standard convention import pandas (SPD). This import statement allows you to access all the functions and classes provided by Pandas using the shorthand PD. To verify that the installation is successful, you can check the version of Pandas by running PD version. This will display the installed version number. Pandas often works in conjunction with other libraries like NumPy, which is used for numerical operations. Together, these tools form the backbone of many data analysis workflows in Python. Two key data structures in Pandas are series and data frame. A series is a one-dimensional labeled array that can hold data of any type, such as integers, strings, or floating point numbers. For example, you can create a series by passing a list of values to the PD. Series function. A data frame, on the other hand, is a two-dimensional structure with rows and columns, much like a spreadsheet. It can be created by passing a dictionary of lists or arrays, or by reading data from external files. One of the advantages of these structures is their ability to handle heterogeneous data types, meaning they can store different types of data in the same structure. Additionally, Pandas allows for labeled indexing, which means you can access data using labels instead of just numerical positions. This makes data manipulation and analysis more intuitive and efficient. Loading data into Pandas is a common task, and the library provides several functions to accomplish this. For example, you can read comma-separated values files using the PD read CSV function. This function is useful for importing data from Excel-like files. Similarly, the PD read Excel function allows you to load data from Excel spreadsheets. If you are working with databases, the PD read SQL function can retrieve data directly from a SQL database. Another option is the PD read JSON function, which is used to load data from JSON files. These functions are designed to handle various file formats and can automatically detect the structure of the data. By using these tools, you can quickly bring external data into your Python environment for further analysis. Data cleaning is a crucial step in any analysis project, and Pandas offers several methods to handle common data issues. One of the most frequent challenges is dealing with missing data. The df drop null function allows you to remove rows or columns that contain missing values, while the df fill null function lets you replace missing values with a specified value. Another important task is removing duplicates, which can be done using the df drop duplicates function. This ensures that your dataset does not contain repeated entries that could skew your results. Additionally, you can convert data types using the df astype function or the PD to data time function for date-related data. Finally, the df rename function helps you update column names to make them more descriptive or consistent with your data. These techniques are essential for preparing clean and reliable datasets for analysis. Exploratory data analysis, or EDA, is the process of examining data to understand its main characteristics. Pandas provides tools to quickly get insights into your data. The df head function displays the first few rows of a data frame, giving you a snapshot of the data. Similarly, the DF tail function shows the last few rows, which is useful for checking the end of the dataset. To summarize the data, the DF describe function generates statistics such as mean, standard deviation, and quartiles. The DF info function provides a concise summary of the data frame, including the data types of each column and the number of non-null values. Finally, you can visualize the data using the DF plot function or integrate it with libraries like Matplotlib and Seaborn for more advanced visualizations. These steps help you identify patterns, anomalies, and relationships within the data. Data manipulation involves transforming and reorganizing data to extract meaningful insights. One common task is filtering rows based on specific conditions. For example, you can use DF column value to select rows where the values in a particular column meet a certain criterion. Sorting data is another essential operation, which can be done with the DF sort values function. This allows you to arrange data in ascending or descending order based on one or more columns. Adding new columns is straightforward by assigning values to a new column name, such as df new column equals df existing, multiplied by a factor. Finally, aggregating data using the DF group by function enables you to compute summary statistics for groups of data. These techniques are fundamental for preparing data for analysis and reporting. Pandas also includes advanced features for more complex data operations. Merging or combining data frames is a common task, and the PD merge function allows you to join two data frames based on a common column or key. Reshaping data involves transforming the structure of a data frame, such as pivoting rows into columns or melting columns into rows. The DF, pivot, and DF melt functions are useful for these tasks. Working with time series data is another area where Pandas excels. The PD to data time function converts data into data time format, and the DF resample function allows you to aggregate data over specific time intervals. Additionally, the DF apply function enables you to apply custom functions to data, making it easier to perform complex transformations. These features make Pandas a versatile tool for handling diverse data challenges. Let's walk through a case study to see how Pandas can be used in practice. Imagine we are analyzing a sample dataset of sales data. First, we would load the data using functions like PD, read, CSV, or PD. read Excel. Next, we would clean the data by handling missing values, removing duplicates, and ensuring the data types are correct. Then, we would perform statistical analysis to calculate metrics such as the mean, median, and correlation between variables. Finally, we would visualize the data using plots to identify trends and patterns. For example, a line chart could show sales trends over time, while a bar chart might compare sales across different regions. This case study demonstrates how pandas can streamline the entire data analysis workflow, from data preparation to visualization. In conclusion, Pandas is an essential tool for anyone working with data in Python. Its intuitive data structures and powerful functions make it easier to handle complex data tasks. Mastering these tools requires practice, so working with real-world datasets is highly recommended. By combining pandas with visualization libraries like Matplotlib and Seaborn, you can gain deeper insights into your data. Whether you are a beginner or an experienced data analyst, Pandas offers the flexibility and functionality to meet a wide range of data analysis needs. Continue exploring its features and applying them to your projects to enhance your skills and efficiency. Data visualization is a critical tool for transforming raw numbers into meaningful insights. By using visual representations, we can quickly identify patterns, trends, and outliers that might be difficult to spot in tables or spreadsheets. This is where Matplotlib and Seaborn come into play. These Python libraries are widely used for creating a variety of plots, from simple line graphs to complex statistical charts. In this session, we will explore the basics of plotting, learn how to customize visualizations to suit our needs, and delve into advanced techniques that can help us uncover deeper information in our data. Whether you are analyzing trends, comparing categories, or exploring relationships, these tools will be essential in your data science journey. Matplotlib is a foundational library for creating static, animated, and interactive visualizations in Python. It provides a flexible framework for generating plots, allowing users to create everything from basic line graphs to intricate 3D visualizations. At the core of Matplotlib are three key components: the figure, which is the overall window or page, the axes, which are the individual plots within the figure, and the plotting functions, which are the tools used to create specific types of graphs. To get started, we use the PLT module, which offers a simple interface for creating plots. For example, PLT plot is used for line graphs, PLT scatter for scatter plots, and PLT bar for bar charts. These functions form the building blocks for more complex visualizations. Seaborn is a Python library built on top of Matplotlib, designed to simplify the creation of statistical visualizations. While Matplotlib provides the foundational tools, Seaborn offers a higher-level interface that makes it easier to generate complex plots. For instance, Seaborn can create heat maps to visualize matrix data, pair plots to explore relationships between multiple variables, and violin plots to compare distributions. One of Seaborn's strengths is its seamless integration with Pandas data frames, allowing users to work with structured data directly. This makes it particularly useful for analysts who frequently work with tabular data, as it reduces the need for extensive preprocessing before plotting. To begin using Matplotlib and Seaborn, we first need to install them. This can be done via pip, the Python package manager, by running the command pip install Matplotlib Seaborn. Once installed, we import the libraries into our code using import Matplotlib, pyplot as PLT, and import Seaborn as SNS. These imports allow us to access the functions and classes provided by the libraries. Additionally, Seaborn offers a built-in function called SNS set that applies a consistent and aesthetically pleasing style to all plots, ensuring that our visualizations look professional and uniform. This step is especially helpful for maintaining a cohesive look across multiple charts in a project. Now, let's explore the basics of plotting with Matplotlib. Line plots, created with PLT plot, are ideal for showing trends over time or ordered categories. Bar charts, generated using PLT bar, are useful for comparing values across different categories. Scatter plots, made with PLT scatter, help visualize the relationship between two variables, such as the correlation between height and weight. Histograms, produced by PLT hist, are used to display the distribution of a single variable, showing how frequently different values occur. These fundamental plot types serve as the foundation for more advanced visualizations and are essential for any data analysis task. Customizing plots is an important step in making them clear and effective. We can start by adding labels to the x-axis and y-axis using PLT, X-label, and PLT, I-label, which help the audience understand what each axis represents. Titles, added with PLT, title, provide a brief description of the plot's purpose. Legends, created with PLT, legend, are useful when multiple data series are displayed, allowing viewers to distinguish between them. Colors can be adjusted using the color parameter or color maps for gradients, which can enhance the visual appeal and clarify the data. For example, using a color map in a scatter plot can indicate a third variable through color intensity. These customization options allow us to tailor our visualizations to the specific needs of our audience. Seaborn excels at creating advanced statistical plots that can reveal deeper insights. Heat maps, generated with SNS. Heat map are excellent for visualizing matrix data, such as correlation matrices, where color gradients represent values. Pair plots, created using SNS. Pair plot are useful for exploring pairwise relationships between variables in a dataset, often used in exploratory data analysis. Violin plots, made with SNS. Violin plot combine elements of box plots and kernel density estimates to show the distribution of data, making it easier to compare multiple groups. These advanced plots are particularly valuable when dealing with complex datasets, as they can highlight patterns and relationships that might not be apparent with simpler visualizations. When creating visualizations, it's important to follow best practices to ensure clarity and effectiveness. First, keep your visuals simple and focused on a single message to avoid overwhelming the viewer. Choose the right plot type based on the data and the question you are trying to answer. For example, use a line plot for trends or a bar chart for comparisons. Clearly label all axes, add titles, and use legends where necessary to guide the audience. To avoid overplotting, especially in scatter plots, techniques like transparency alpha parameter or jitter, adding small random noise, can help distinguish overlapping points. These practices ensure that your visualizations are both informative and easy to interpret. Let's apply these concepts to a real-world example. We'll start by loading the tips dataset, which includes information about restaurant bills and tips. Using Seaborn's bar plot function, we can create a bar chart that shows the average total bill for each day of the week. This helps us see if there are any patterns in spending habits. We'll then add customization by setting a title to describe the plot, adjusting the colors to make it more visually appealing, and including grid lines to improve readability. This example demonstrates how Matplotlib and Seaborn can be used together to create informative and polished visualizations that effectively communicate insights from the data. In conclusion, Matplotlib and Seaborn are indispensable tools for data visualization in Python. They offer a wide range of functionalities, from basic plotting to advanced statistical analysis. By practicing the techniques discussed, you can create clear and impactful visualizations that enhance your data analysis. Remember to explore different data sets and experiment with various plot types to find the most effective way to present your findings. As you gain more experience, you'll be able to leverage these libraries to uncover new insights and communicate your results with confidence. Web development involves creating interactive websites and applications that users can access through the internet. At its core, it requires understanding how servers and clients communicate, how data is processed, and how to design user-friendly interfaces. Python has become a dominant force in modern web development due to its simplicity, versatility, and a rich ecosystem of libraries. Flask, a lightweight framework, plays a crucial role in this landscape by providing developers with the tools to build web applications efficiently without unnecessary complexity. Flask is a micro-framework designed for Python developers who want to create web applications with minimal overhead. Unlike larger frameworks that impose strict structures, Flask prioritizes simplicity and flexibility, allowing developers to choose the tools and libraries that best suit their projects. This makes it ideal for small to medium-sized applications, prototyping, or scenarios where customizability is essential. Its lightweight nature ensures fast performance while maintaining a straightforward learning curve. One of Flask's defining characteristics is its minimalist design, which means it does not include built-in tools for tasks like database management or object relational mapping. This approach gives developers full control over their application's architecture. However, Flask supports extensions that add functionality, such as Flask SQL Alchemy for database integration, or Flask WTF for form validation. This modularity ensures that developers can tailor their applications to specific needs while leveraging community-driven extensions for advanced features. To begin working with Flask, you first need to install Python and pip, the package manager for Python. Once Python is set up, you can install Flask by running the command pip install Flask in your terminal or command prompt. After installation, verify it by checking the version with Flask version. This step ensures that your environment is correctly configured and ready to build web applications. Creating a basic Flask application starts with importing the Flask class from the Flask module. You then initialize an instance of the Flask class, typically using the name of the current module as the argument. Roots are defined using decorators, such as at app_root, which maps a URL to a function. Finally, the app is run using the app_run method, which starts the development server and makes your application accessible through a web browser. In Flask, roots act as the bridge between URLs and the functions that handle them. For example, a root like at app_root hello will trigger a specific function when a user visits the hello URL. Dynamic roots allow for more flexibility by including parameters such as at app route/user/name, which captures a user's name from the URL and passes it to the corresponding function. This enables personalized responses based on user input. Flask uses the Genia 2 templating engine to generate dynamic HTML content. Templates allow you to separate the presentation logic from the application code, making it easier to manage and update. By using the render template function, you can pass variables from your Python code to the HTML template, which then renders the final output. This approach is essential for creating interactive and data-driven web pages. Handling HTTP requests and responses is a fundamental aspect of web development. Flask supports methods like GET for retrieving data and POST for submitting forms. The request object provides access to data sent by the client, such as form inputs or query parameters. Responses can be returned as rendered templates or in JSON format using JSONify, making it easy to build APIs or dynamic web interfaces. Organizing a Flask application effectively is key to maintaining scalability and readability. A typical structure includes an app.py file for the main application logic, a templates folder for HTML files, and a static folder for assets like CSS and JavaScript. For larger projects, blueprints help modularize the code base, while configuration files store settings like secret keys or database connections. This structure ensures that the application remains manageable as it grows. Following best practices in Flask development ensures that your applications are secure, maintainable, and efficient. Using virtual environments isolates dependencies, preventing conflicts between projects. Security is critical, so implementing authentication, validating user input, and protecting against common vulnerabilities like SQL injection is essential. Adhering to PEP 8 guidelines for code style improves readability and collaboration, making your code base more professional and easier to work with. Flask provides a solid foundation for building web applications, but its true potential lies in exploring advanced topics like integrating databases, creating REST-TFL APIs, and deploying applications to production environments. Practicing by building real-world projects, such as a blog or to-do list, reinforces your understanding and helps you apply concepts in meaningful ways. As you progress, you'll discover how Flask's flexibility and community support make it a powerful tool for web development. Web applications are software applications that run on a web server and are accessed through a web browser. They consist of several key components, including the front end, which is the user interface, the back end, which handles data processing and business logic, and the database, which stores and retrieves data. Python plays a significant role in web development due to its simplicity and the availability of powerful frameworks. Frameworks like Flask and Django provide structured tools and libraries that streamline the development process. Flask is a lightweight framework ideal for small to medium applications, while Django offers a more robust set of features for larger projects. These frameworks handle many of the complexities of web development, allowing developers to focus on building unique functionality. Understanding these tools is essential for anyone looking to create dynamic and interactive web applications. To begin building a web application with Python, the first step is to install Python and a web framework such as Flask. Python can be downloaded from the official website, and Flask can be installed using a package manager like pip. It is also important create a virtual environment for each project to isolate dependencies and avoid conflicts between different projects. A virtual environment ensures that the specific libraries and versions required for a project are contained within that environment. Once the environment is set up, a basic project structure should be created. This typically includes an app .py file to hold the application code, a templates folder for HTML files, and a static folder for CSS, JavaScript, and image files. This organization helps maintain a clean and manageable code base. Creating a basic Flask application involves a few straightforward steps. First, import the Flask class from the Flask module and initialize the application by creating an instance of the Flask class. This instance, often named app, serves as the central object for the application. Next, define a route for the home page by using the @app route decorator, which maps a URL to a function. For example, the route will trigger a function that returns a response when the user visits the route URL. Finally, run the development server by calling the app_run method. This starts a local server, allowing you to test the application in a browser. However, it is important to note that the development server is not suitable for production environments and should only be used during testing. Expanding on a basic Flask application, adding multiple routes allows the application to handle different URLs and serve distinct content. For instance, a route like @app route about can display an about page. To create dynamic web pages, Flask uses Jinja 2 templating, which enables the embedding of variables and logic within HTML files. By passing variables from Python to templates, the content can be customized based on data. For example, a variable named username can be passed to a template, and the template can display a personalized message. This dynamic capability enhances user interaction and makes the application more responsive to different inputs. Understanding how to structure and use templates is crucial for building visually appealing and functional web applications. Handling user input is a critical aspect of web development, as it allows applications to respond to user actions. This is typically done through HTML forms, which collect data from users and send it to the server. In Flask, form data can be processed using the post method, which is more secure than the GET method for sensitive information. When a form is submitted, the server receives the data through the request object, which can then be validated and sanitized to prevent malicious attacks. Validation ensures that the data meets specific criteria, such as correct format or length, while sanitization removes potentially harmful content. Proper handling of user input is essential for maintaining the security and reliability of a web application. Styling a web application involves organizing static files such as CSS, JavaScript, and images in a dedicated static folder. These files are essential for enhancing the visual appearance and functionality of the application. In Flask, static files are accessed using the urlfor function, which generates the correct URL for a given file. For example, urlfor static, file name equals styles, CSS links to a CSS file in the static folder. By using this function, the application can dynamically reference files without hard-coding their paths. Basic styling techniques, such as applying colors, fonts, and layout adjustments, can significantly improve the user experience. A well-styled application not only looks more professional, but also makes it easier for users to navigate and interact with the content. Deploying a web application makes it accessible to users over the internet. There are several options for deployment, including platforms like Heroku and Python Anywhere, which provide easy-to-use services for hosting Python applications. When deploying, it is important to configure environment variables to store sensitive information such as API keys or database credentials. Additionally, dependencies must be properly managed by creating a requirements TXT file that lists all the packages required by the application. After deployment, thorough testing is necessary to ensure that the application functions correctly in the production environment. This includes checking for errors, verifying that all features work as intended, and ensuring that the application can handle expected traffic. Successful deployment is the final step in making a web application available to a broader audience. In summary, building a simple web application with Python involves understanding the components of web development, setting up the environment, and utilizing frameworks like Flask to streamline the process. Frameworks such as Flask and Django provide essential tools that reduce the complexity of coding, allowing developers to focus on creating unique features. As you continue your journey in web development, exploring advanced topics such as integrating databases for persistent data storage or implementing user authentication, will further enhance your skills. These next steps will enable you to build more sophisticated and secure applications. With practice and exploration, you can expand your knowledge and create powerful web solutions that meet diverse user needs. A database is essentially a structured collection of data that allows for efficient storage, retrieval, and management of information. Think of it as a digital filing cabinet where data is organized in a way that makes it easy to access and update. This structure is typically achieved through tables, which are made up of rows and columns. Each row represents a unique record, while each column defines a specific attribute of that record. For example, in a table storing customer information, a row might represent a single customer, and the columns could include details like their name, email address, and phone number. Popular examples of database systems include relational databases like MySQL, PostgreSQL, and SQLite, as well as non-relational or NoSQL databases like MongoDB. These systems cater to different needs, from handling complex queries to managing large volumes of unstructured data. Databases play a crucial role in modern applications by enabling efficient data organization and scalability. As data grows, a well-designed database ensures that information can be accessed and managed without performance degradation. They support complex queries, allowing users to extract specific information from vast datasets. For instance, a bank might use a database to quickly retrieve a customer's transaction history. Data integrity is another key benefit, as databases enforce rules to prevent inconsistent or incorrect data from being stored. They also facilitate multi-user access, ensuring that multiple people can interact with the same data simultaneously while maintaining security. This makes databases essential for applications like banking systems, e-commerce platforms, and social media networks, where reliability and data accuracy are paramount. To interact with relational databases, we use a language called SQL, which stands for Structured Query Language. SQL is the standard tool for managing and manipulating data stored in relational databases. It allows users to perform a wide range of operations, from querying data to updating and deleting records. For example, a developer might use SQL to retrieve a list of products from a database, or to add a new user to a system. Common SQL operations include select, which is used to fetch data, insert, which adds new records, update, which modifies existing data, and delete, which removes records. Additionally, SQL includes commands like create and drop to manage database structures. These operations form the foundation of working with relational databases and are essential for anyone looking to build data-driven applications. Understanding SQL syntax is the first step in interacting with databases. The basic structure of a select statement, for instance, is select column from table where condition. This allows you to specify which data you want to retrieve from which table and under what conditions. For example, select name from customers where city equals New York would fetch the names of all customers located in New York. Inserting data into a table follows a similar pattern. Insert into table columns values. This command adds a new record to the specified table. Updating existing data uses the update statement, such as update table set column equals value where condition, which modifies specific records. Finally, the delete statement, delete from table where condition, removes records that meet a certain criterion. Mastering these syntax patterns is critical for effectively managing data in a relational database. Relational databases are designed to store data in multiple tables that are linked by relationships. This approach allows for efficient data organization and reduces redundancy. For example, a user's table might store information about registered users, while an orders table keeps track of their purchases. These tables are connected through a relationship, often using a primary key in one table and a foreign key in another. A primary key is a unique identifier for each record in a table, ensuring no duplicates. A foreign key, on the other hand, is a field in one table that links to the primary key of another table, establishing a connection between them. Normalization is another important concept in relational databases, which involves structuring data to minimize duplication and improve integrity. By organizing data into related tables, relational databases provide flexibility and scalability for complex applications. Python, a versatile programming language, integrates seamlessly with databases through various libraries and tools. For example, the SQLite 3 module allows Python to interact with SQLite databases, which which are lightweight and file-based. For more robust systems, libraries like MySQLDB and Scicop2 enable connections to MySQL and PostgreSQL databases, respectively. These libraries provide functions to execute SQL queries, fetch results, and manage database transactions. In addition to direct SQL interactions, Python developers often use object relational mapping (ORM) tools like SQL Alchemy. ORMs abstract the complexity of SQL by allowing developers to work with databases using Python objects, making it easier to perform operations like querying and updating data. This integration empowers Python to handle dynamic data in applications ranging from web development to data analysis. Connecting to a database in Python involves several key steps. First, you import the appropriate module, such as SQLite 3 for SQLite databases. Next, you establish a connection using the connect function, which creates a link to the database file or server. Once connected, a cursor object is created to execute SQL commands. The cursor acts as a pointer to the database, allowing you to run queries and retrieve results. For example, after creating a cursor, you might use its execute method to run a select statement. After completing your operations, it is important to close the connection to free up resources and prevent potential issues like memory leaks. Properly managing these steps ensures that your Python application interacts with the database efficiently and securely. Basic SQL queries are fundamental for retrieving and manipulating data in a database. The simplest query is select from customers, which retrieves all records from the customers table. This is useful when you need to view all available data, though it may not be efficient for large data sets. To filter results, you can use the where clause, as in select name from customers, where city equals New York. This query fetches only the names of customers located in New York. Sorting results is another common task, achieved with the order by clause. For instance, select from orders order by date desk would return orders sorted by date in descending order, showing the most recent first. These basic queries form the foundation for more complex data interactions and are essential for any database user. CRUD operations create, read, update, and delete are the core functions for managing data in a database. The create operation adds new data such as inserting a new user into a user's table with insert into user's name. Email values Alice. Alice@example.com. The read operation retrieves existing data, like select from users, which displays all user records. The update operation modifies existing data, for example, changing a user's email address with update users set email equals Alisanu@example.com, where id equals 1. Finally, the delete operation removes data, as seen in delete from users, where id equals 1, which deletes the user with ID 1. These operations are the building blocks for interacting with databases and are essential for developing applications that require dynamic data handling. In summary, databases are vital for organizing and managing large datasets efficiently. They provide a structured way to store, retrieve, and update information, making them indispensable for modern applications. SQL is the standard language for working with relational databases, enabling users to perform a wide range of data operations. Python's ability to interact with databases through libraries and ORMs makes it a powerful tool for developers. Whether you're building a simple app or a complex system, understanding databases and SQL is crucial for success. To master these concepts, practice writing SQL queries and experimenting with Python's database integration features. The more you engage with these tools, the more proficient you'll become in handling real-world data challenges. Connecting Python to databases is essential for managing and accessing data efficiently. Whether you're building a simple application or a complex system, databases allow you to store, retrieve, and manipulate data effectively. Two common database systems we will explore are SQLite and MySQL. SQLite is a lightweight, file-based database ideal for small projects, while MySQL is a powerful relational database management system suited for larger applications. By the end of this presentation, you will learn how to establish connections, execute queries, and manage databases using Python. SQLite is a self-contained, serverless database engine that stores data in a single file. This makes it incredibly easy to use because there is no need to install or configure a separate server. It is perfect for applications that require a simple and portable solution, such as mobile apps or small desktop programs. Python includes a built-in module called SQLite 3 that provides a straightforward interface for interacting with SQLite databases. This means you can start working with SQLite immediately without installing additional libraries. To connect to an SQLite database, you use the SQLite 3 connect method, passing the name of the database file. If the file does not exist, it will be created automatically. For example, the code con SQLite 3 connect example DB establishes a connection to a database named example DB. Once connected, you need to create a cursor object, which acts as a pointer to the database and allows you to execute SQL commands. This cursor is essential for performing operations like creating tables or querying data. Once you have a connection and a cursor, you can execute SQL commands using the cursor execute method. For instance, the command cursor execute create table, if not EXISTS users, id integer primary key name text, creates a table called users if it does not already exist. After executing commands that modify the database, you must call con, commit to save the changes. Finally, always close the connection with con, close to free up resources and ensure data integrity. These steps are crucial for maintaining a reliable database interaction. MySQL is a robust relational database management system that operates on a client-server model. Unlike SQLite, it requires a dedicated server to run, making it suitable for applications that need to handle multiple users or large amounts of data. MySQL is widely used in web development and enterprise environments due to its scalability and advanced features. To interact with MySQL from Python, you can use libraries such as MySQL Connector Python or PyMySQL. These drivers enable communication between Python and the MySQL server, allowing you to perform complex database operations. Before connecting to a MySQL database, you need to install the appropriate driver. For example, using pip install MySQL Connector Python installs the necessary package. Once installed, you can establish a connection by providing the server's credentials, such as the username, password, host, and database name. An example connection string is con equals MySQL, connector, connectuser equals root, password equals password, host equals localhost, database equals MyDB. This creates a connection to a local MySQL server running on the same machine. After connecting, you can create a cursor and execute SQL commands just as you would with SQLite. With MySQL, you can perform a variety of operations, including creating, reading, updating, and deleting data. For example, the command cursor execute select from users retrieves all records from the users table. To access the results, you can use methods like cursor fetch all to get all rows or cursor fetch on to retrieve a single row. These functions allow you to process data efficiently, whether you're displaying it to a user or performing further analysis. Understanding these operations is key to building dynamic applications that interact with databases. SQLite and MySQL have distinct characteristics that make them suitable for different scenarios. SQLite is serverless and stores data in a single file, making it ideal for prototyping or applications with minimal requirements. MySQL, on the other hand, requires a server and is designed for scalability, making it a better choice for production environments. While SQLite is easier to set up, MySQL offers advanced features like user management and concurrent access. Choosing the right database depends on your project's size, complexity, and performance needs. Adhering to best practices ensures your database interactions are secure and efficient. Always use parameterized queries to prevent SQL injection attacks, which can compromise your data. For example, instead of directly inserting user input into a query, use placeholders and pass values separately. Additionally, make sure to close database connections after use to avoid resource leaks. Implementing try-except blocks in your code helps handle exceptions gracefully, ensuring your application remains stable even when errors occur. These practices are essential for maintaining reliable and secure database operations. In conclusion, Python provides powerful tools for connecting to both SQLite and MySQL databases, enabling you to manage data effectively. By understanding how to establish connections, execute queries, and perform database operations, you can build applications that handle data dynamically. Applying best practices, such as using parameterized queries and proper error handling, ensures your code is both secure and efficient. As you continue learning, experimenting with both databases will deepen your understanding and help you choose the right tool for your projects. Decorators are a powerful feature in Python that allow you to modify the behavior of functions or classes without changing their actual code. Think of them as functions that take another function as input and return a new function that extends or alters its functionality. The @ symbol is used to apply a decorator to a function or class, making the syntax clean and readable. For example, when you use its static method or at property, you're leveraging decorators to change how a method behaves. Common use cases include adding logging to track when a function is called, timing how long a function takes to execute, or controlling access to a method based on certain conditions. Decorators can even be chained together, meaning you can apply multiple decorators to a single function, each contributing its own modification. This makes decorators a versatile tool for writing modular and reusable code. To understand how decorators work, imagine a function that takes another function as an argument and returns a new function. This is the core concept behind decorators. The syntax is straightforward. You place the @ symbol followed by the decorator name directly above the function definition. For instance, if you have a function called myFunction, you can apply a decorator by writing a decorator name before it. This is equivalent to wrapping the function in the decorator, which then returns a modified version of it. Decorators are not limited to simple functions. They can also be applied to class methods, such as static methods or properties, to change their behavior. Additionally, decorators can accept parameters, allowing for more flexible and customized modifications. This means you can create decorators that adapt based on the arguments provided, making them even more powerful for different use cases. Let's explore some practical examples of decorators in action. One common use is logging, where a decorator can automatically record details like the function name, arguments, or return values. This is incredibly useful for debugging or monitoring the flow of a program. Another application is timing, where a decorator measures how long a function takes to execute, helping identify performance bottlenecks. Access control is another area where decorators shine, such as checking if a user has the necessary permissions before allowing a method to run. Finally, caching is a technique where a decorator stores the results of expensive function calls. So repeated calls with the same arguments can retrieve the cached result instead of recalculating it. These examples demonstrate how decorators can simplify complex tasks and improve the efficiency and maintainability of your code. Generators are a special type of function in Python that produce values one at a time, rather than returning them all at once. Instead of using the return statement, generators use the yield keyword to pause and resume their execution. This makes them ideal for handling large datasets or infinite sequences, as they don't need to store all the data in memory at once. For example, if you have a generator that yields numbers from 1 to 100, it will produce each number on demand, rather than creating a list of all 100 numbers up front. Generators are also iterable, meaning you can loop through their values, and they support lazy evaluation, which means they only compute values when needed. This makes them highly efficient for scenarios where memory usage is a concern, such as processing large files or generating sequences that could theoretically be infinite. When a generator function is called, it doesn't execute immediately. Instead, it returns an iterator object that can be used to retrieve values one at a time. Each time you call the next function on this iterator, the generator resumes execution from where it last yielded a value. For example, if you have a generator function called count that yields 1, then 2, and then 3, the first call to next will return 1, the second call will return 2, and so on. This behavior is what makes generators so efficient for handling large or streaming data. You can also use generators in for loops, where each iteration automatically calls next for you. Additionally, generators can be converted into lists if needed, but their true power lies in their ability to produce values on the fly, reducing memory overhead and improving performance. Generators are particularly useful in scenarios where memory efficiency is critical. For instance, when processing large files, a generator can read and yield one line at a time, preventing the entire file from being loaded into memory. This is especially important when dealing with files that are too large to fit in RAM. Generators can also be used to create custom iterators, allowing you to define your own logic for generating values. Another common use case is generating infinite sequences, such as the Fibonacci sequence, where the generator can produce numbers indefinitely without running out of memory. Compared to lists, generators are much more memory efficient, as they don't store all the elements at once. This makes them a go-to solution for handling data streams, real-time processing, or any situation where you need to work with a large volume of data without excessive memory usage. While decorators and generators both enhance Python's capabilities, they serve different purposes. Decorators are used to modify the behavior of functions or classes, often adding functionality like logging, timing, or access control. They act as a wrapper around the original function, altering its behavior without changing its code. On the other hand, generators are designed to produce a sequence of values on demand, making them ideal for handling large data sets or infinite sequences. Decorators focus on extending functionality, while generators focus on efficient data iteration. However, these two concepts can be combined to achieve even better results. For example, you might use a decorator to add logging to a generator function, or use a generator within a decorated function to optimize performance. Understanding both decorators and generators allows you to write more flexible and efficient Python code. In conclusion, decorators and generators are essential tools for any Python programmer. Decorators enable you to write modular and reusable code by extending the functionality of functions and classes without altering their original code. They make it easy to add features like logging, timing, and access control. Generators, on the other hand, provide an efficient way to iterate through large data sets or create infinite sequences without consuming excessive memory. Mastering these concepts will significantly improve your ability to write clean, efficient, and scalable Python programs. The best way to solidify your understanding is to practice implementing custom decorators and generators in your own projects. By experimenting with these features, you'll gain a deeper appreciation for how they can enhance your code and solve real-world problems. Good morning. Today, we will explore the fascinating world of concurrency and multi-threading in Python. Concurrency refers to the ability of a program to handle multiple tasks in overlapping periods. Think of it as a way to manage several activities at once without waiting for one to finish before starting another. Multi-threading takes this a step further by using multiple threads within a single process. Each thread can perform a separate task, allowing for more efficient resource utilization. This is particularly important in Python for I/O-bound tasks, such as handling network requests or file operations, and for maintaining responsiveness in GUI applications. By the end of this session, you will have a clear understanding of threading concepts and how to implement them effectively. Let's now distinguish between concurrency and parallelism. Concurrency is about the interleaving of tasks, where the program switches between them to create the illusion of simultaneous execution. This is different from parallelism, which involves true simultaneous execution of tasks, typically requiring multiple CPUs or cores. In Python, the Global Interpreter Lock, or GIL, plays a crucial role here. The GIL ensures that only one thread executes at a time, even on multi-core systems. This limitation means that for CPU-bound tasks, Python does not achieve true parallelism. However, the GIL simplifies memory management and prevents certain types of race conditions, making it a trade-off worth understanding. Why should we use multi-threading in Python? The answer lies in its efficiency for I/O-bound tasks. For example, when a program is waiting for data from a network or a file, the thread can yield control to other tasks, preventing the application from freezing. This is vital for keeping user interfaces responsive, such as in web servers that handle multiple requests simultaneously. Another advantage is that threads within the same process share the same memory space, allowing for easy data exchange between them. However, this shared memory also requires careful handling to avoid conflicts, which we will discuss later. Let's delve deeper into the Global Interpreter Lock. The GIL is a mechanism in CPython that ensures only one thread executes Python bytecode at a time. This design choice was made to simplify memory management and avoid the complexities of thread safety. While the GIL prevents true parallelism for CPU-bound tasks, it does not hinder I/O-bound tasks, as threads can release the GIL during waiting periods. For example, a thread performing a network request will relinquish the GIL, allowing other threads to run. However, for tasks that require heavy computation, such as numerical processing, the GIL can become a bottleneck, leading to performance limitations. Now, let's discuss how to implement multi-threading in Python using the threading module. The first step is to import the module, which provides the necessary tools for creating and managing threads. To start a thread, you create a thread object and pass it a target function along with any arguments. The start method initiates the thread, and the join method ensures the main program waits for all threads to complete before proceeding. This structure allows for controlled execution and synchronization of multiple threads. Here's a simple example to illustrate these concepts. Imagine two threads printing messages to the console. The code begins by importing the threading module. A function called printMessage is defined to accept a message and print it. Two thread objects are created, each targeting this function with a different argument. When the start method is called on both threads, they begin execution. However, the order in which the messages appear depends on the thread scheduler, which is managed by the operating system. This variability highlights the non-deterministic nature of thread execution. Thread synchronization is essential to prevent issues like race conditions. A race condition occurs when multiple threads access shared resources simultaneously, leading to unpredictable results. To address this, Python provides the threading lock class. A lock ensures that only one thread can execute a critical section of code at a time. For example, if two threads attempt to modify a shared counter, acquiring a lock before the operation prevents conflicts. After completing the critical section, the lock is released, allowing other threads to proceed. Proper use of locks is crucial to avoid deadlocks, where threads wait indefinitely for resources. Multi-threading comes with its challenges. One of the most common is race conditions, which can corrupt data if not managed carefully. Deadlocks are another concern, where threads become stuck waiting for each other to release resources. Ensuring thread safety requires designing code that handles shared data correctly. For instance, using locks or thread-safe data structures can mitigate these issues. Understanding these challenges is key to writing robust and reliable multi-threaded applications. To make the most of multi-threading, follow these best practices. Minimize the use of shared data between threads to reduce the risk of conflicts. When necessary, use synchronization mechanisms like locks or queues to manage access to shared resources. The Concurrent Futures module offers a higher-level interface for thread management, simplifying tasks like parallel execution. Finally, remember that multi-threading is not ideal for CPU-bound tasks. In such cases, the multiprocessing module is a better choice, as it bypasses the GIL by using separate processes. In summary, concurrency and multi-threading are powerful tools for improving the responsiveness of I/O-bound applications. Understanding the limitations of the GIL and the importance of synchronization is essential for effective threading. Use multi-threading for tasks like network requests or GUI updates, and opt for multiprocessing when dealing with CPU-intensive workloads. By applying these principles, you can build efficient and scalable Python applications that make the most of modern computing resources. Thank you for your attention, and I hope this session has deepened your understanding of threading in Python. Functional programming is a programming paradigm that focuses on writing code using pure functions and immutability. Unlike imperative programming or object-oriented programming, which rely on changing state and mutable data, functional programming emphasizes declarative code. This means that instead of telling the computer how to perform a task step by step, you describe what the task is. For example, in functional programming, functions avoid side effects, meaning they do not alter external variables or data. This approach makes code more predictable and easier to reason about. Key concepts in functional programming include higher-order functions, which are functions that can take other functions as arguments or return them as results. Recursion, which is when a function calls itself to solve a problem. And lambda expressions, which are small, anonymous functions used for short operations. These tools allow developers to write concise and expressive code. A pure function is a function that has no side effects and always returns the same output for the same input. This means that a pure function does not modify any external state or variables outside its scope. For instance, if you have a function called add that takes two numbers and returns their sum, it will always produce the same result given the same inputs. This consistency makes pure functions easier to test and debug because you don't have to worry about unexpected changes in variables or external dependencies. In contrast, impure functions might alter global variables, interact with the file system, or rely on external data, making their behavior harder to predict. By using pure functions, you can create more reliable and maintainable code. Immutability is a core principle in functional programming, which means that once data is created, it cannot be changed. In Python, this is achieved through data structures like tuples, strings, and frozen sets. For example, if you have a tuple like 1, 2, 3, you cannot modify its elements directly. Instead, you create a new tuple by combining it with additional elements, such as 1, 2, 3 plus 4. This approach ensures that data remains consistent and avoids unintended modifications. Immutability also makes code safer for parallel processing because multiple threads or processes can access the same data without worrying about conflicting changes. While immutable data structures can sometimes lead to performance trade-offs, such as creating new objects for every change, the benefits of predictability and reduced bugs often outweigh these costs. Higher-order functions are functions that can accept other functions as arguments or return them as results. This concept allows for more flexible and reusable code. In Python, built-in functions like map, filter, and reduce are examples of higher-order functions. The map function applies a given function to each item in an iterable, such as a list. For instance, using map with a lambda function to multiply each element in a list by 2. The filter function, on the other hand, selects elements from an iterable based on a condition. The reduce function, which is part of the functools module, applies a function cumulatively to the items of an iterable, reducing them to a single value. These tools enable developers to write concise and expressive code by abstracting common operations into reusable functions. Recursion is a technique where a function calls itself to solve a problem by breaking it into smaller, more manageable subproblems. This approach is particularly useful for tasks that can be naturally divided into similar subtasks, such as calculating factorials or traversing tree structures. For example, a recursive factorial function would check if the input is 0 and return 1, otherwise multiplying the input by the factorial of the input minus 1. However, Python has a recursion depth limit, which means that very deep recursion can lead to stack overflow errors. Therefore, recursion is best suited for problems with a manageable depth. While recursion can make code more elegant, it is important to ensure that each recursive call moves closer to a base case to avoid infinite loops. Lambda functions are small, anonymous functions defined using the lambda keyword. They are often used for short, inline operations where a full function definition would be unnecessary. The syntax for a lambda function is lambda arguments, expression, where the expression is evaluated and returned. For example, a lambda function can be used to square a number by writing lambda x squared. These functions are particularly useful when passing simple functions as arguments to higher order functions like map or filter. However, Lambda functions should not be overused for complex logic, as they can reduce code readability. Their simplicity makes them ideal for situations where a quick, one-time operation is needed without the overhead of defining a named function. Functional programming offers several benefits that can improve code quality and maintainability. One of the most significant advantages is simpler debugging, because pure functions produce consistent outputs for given inputs, making it easier to trace and fix issues. Testing is also more straightforward, since functions do not rely on external state, allowing for isolated unit tests. Immutability further enhances safety in parallel processing, as shared data cannot be modified unexpectedly by multiple threads. Additionally, higher-order functions promote code reusability by enabling developers to create generic functions that can be adapted to different use cases. By leveraging these principles, Python developers can write cleaner, more predictable, and more maintainable code. While functional programming has many advantages, it is important to recognize its limitations in Python. Python is not a purely functional language, and developers often mix paradigms to achieve their goals. This means that concepts like side effects and mutable data are still prevalent in Python code. Recursion, while powerful, can lead to Stack Overflow errors if not used carefully, especially for large input sizes. Additionally, immutability can introduce performance trade-offs, as creating new data structures for every change may be less efficient than modifying existing ones. These challenges require careful consideration when applying functional programming principles. Developers must weigh the benefits of purity and immutability against practical constraints like performance and code complexity. In conclusion, functional programming emphasizes writing clean, predictable code through the use of pure functions, immutability, and higher-order functions. Key tools in Python include lambda expressions for short, inline operations, map and filter for transforming and filtering data, and the concept of immutability to ensure data consistency. While Python is not a purely functional language, integrating these principles can significantly improve code clarity and maintainability. Functional programming complements object-oriented programming by offering alternative approaches to problem solving. By practicing and applying these concepts, developers can create more robust and scalable applications. embracing functional programming requires a shift in mindset. But the benefits of predictable code and easier debugging make it a valuable skill for any Python programmer. Pythonic code is about writing in a way that feels natural to those who work with Python. It emphasizes clarity, simplicity, and readability, which makes the code easier to understand and maintain. Instead of forcing patterns from other programming languages, Pythonic code follows the idioms and conventions that are common in the Python community. For example, using list comprehensions for simple iterations, or leveraging the power of built-in functions can make the code more concise and expressive. The goal is to write code that not only works correctly, but also aligns with the expectations of Python developers, fostering better collaboration and long-term project sustainability. Following PEP 8 guidelines is essential for maintaining a consistent and professional code base. PEP 8 specifies that indentation should be 4 spaces, which helps in visually structuring code blocks. Line length should not exceed 79 characters, ensuring that code remains readable without horizontal scrolling. Spacing around operators and after commas adds to the visual clarity. For instance, writing calculate average instead of AVG makes the code more self-explanatory, avoiding unnecessary white space and ensuring consistent formatting reduces the cognitive load when reading code, especially in team environments where multiple developers contribute to the same project. Prioritizing readability over cleverness is a key principle in Pythonic code. While it might be tempting to write compact one-liners, such as using complex list comprehensions or nested functions, this can often obfuscate the code's purpose. Simple and explicit code is easier to debug and modify. For example, a loop that calculates an average step by step is clearer than a single line that combines multiple operations. Comments should explain the reasoning behind complex logic, such as "this handles edge case X," to clarify why a particular approach is used. Avoiding overuse of advanced features ensures that the code remains accessible to all team members, regardless of their expertise level. Python offers a rich set of built-in functions and libraries that can significantly enhance code efficiency and readability. Functions like map, filter, and zip allow for concise and expressive data manipulation. For instance, using map to apply a function to all elements in a list is more elegant than than writing a manual loop. Standard libraries, such as ITER tools and collections, provide tools for handling common tasks without reinventing the wheel. Instead of writing a loop to sum numbers, using sum is not only shorter, but also more efficient because it is implemented in C. Leveraging these tools reduces the risk of errors and makes the code more maintainable. Avoiding anti-patterns is crucial for writing clean and scalable code. Excessive nested loops or deep conditionals can lead to complex and hard-to-maintain code. For example, a loop inside another loop might work for small data sets, but can become a performance bottleneck. Using import can cause namespace conflicts, making it difficult to track where a particular function or variable comes from. Hard-coding values like 5 or 100 directly into the code makes it less flexible. Instead, using constants or configuration files allows for easier updates and reduces the risk of bugs. These practices help in creating code that is both robust and adaptable. Naming conventions in Python are a cornerstone of readability. Variables should be named using snake case, such as username, to clearly indicate their purpose. Classes, on the other hand, use Pascal case, like data processor, to distinguish them from functions and variables. Constants, which are values that do not change, are written in uppercase, such as maxaritris. These conventions create a visual structure that helps developers quickly understand the role of each element in the code. Consistent naming reduces confusion and makes the code base more approachable for new contributors. Docstrings and comments are vital for explaining the purpose and functionality of code. Writing docstrings for modules, functions, and classes using triple quotes provides a clear description of what the code does and how to use it. For example, a function's docstring might explain its parameters and return values. Comments should focus on explaining the why rather than the what, such as avoid none for default, to clarify the reasoning behind a design choice. Keeping comments concise and up-to-date ensures that they remain helpful and do not become outdated as the code evolves. This practice is especially important in collaborative projects where others may need to understand and modify the code. Error handling is a critical aspect of writing robust Python code. Using try-except blocks allows developers to anticipate and manage exceptions gracefully. For instance, catching a value error when converting a string to an integer prevents the program from crashing unexpectedly. Avoiding bare except clauses is essential because they can suppress errors that should be addressed. Logging or handling errors explicitly ensures that issues are visible and can be resolved. This practice not only improves the user experience, but also makes debugging easier by providing clear information about what went wrong. Testing and debugging are essential for ensuring code reliability. Writing unit tests using frameworks like Unitist or Pytest helps verify that critical logic works as intended. For example, a test case might check if a function returns the correct result for a given input. Using print statements or debuggers like PDB allows developers to trace the flow of execution and identify issues. Testing edge cases and invalid inputs ensures that the code can handle unexpected scenarios without failing. This proactive approach to testing builds confidence in the code's correctness and reduces the likelihood of bugs in production. In conclusion, Pythonic code enhances maintainability and collaboration by adhering to best practices and leveraging Python's strengths. Following PEP 8 guidelines, prioritizing readability, and using built-in functions and libraries are key steps in writing clean, idiomatic code. Practicing these habits consistently helps developers create code that is not only functional, but also easy to understand and extend. By focusing on clarity and simplicity, Python developers can build applications that are robust, scalable, and welcoming to others. Testing ensures code works as expected by verifying that functions and modules perform their intended tasks under various conditions. Debugging identifies and fixes errors in code, which is crucial for maintaining the integrity of Python applications. Both practices are essential for building reliable software, as they help catch issues early and prevent unexpected behavior. By prioritizing testing and debugging, developers can significantly reduce the number of bugs and improve the overall quality of their code. Testing is vital because it validates functionality across different scenarios, ensuring that code behaves correctly even in complex or unusual situations. It prevents regressions, which occur when changes to code unintentionally break existing features. Testing also facilitates collaboration in team projects by providing a shared understanding of how code should work. Additionally, it allows developers to refactor code with confidence, knowing that tests will catch any unintended side effects. In Python, there are several types of testing. Unit testing focuses on individual functions or methods, ensuring each component works independently. Integration testing examines how different parts of the application interact, which is critical for identifying issues in combined systems. System testing evaluates the entire application as a whole, simulating real-world usage. Regression testing ensures that new code does not introduce errors in previously working features, maintaining stability over time. Python offers multiple testing frameworks to choose from. The Unitist framework is built into the standard library and provides a structured way to write test cases. PyTest is a third-party tool known for its simplicity and scalability, allowing developers to write concise tests. Doctist enables testing by embedding examples directly in docstrings, making it easy to validate documentation. Nose 2 extends Unitist with additional features, such as automatic test discovery and more flexible test organization. Writing unit tests in Python involves creating test classes that inherit from Unitist. Test case. Each test method should start with the prefix test to be recognized by testing frameworks. Common assertions like assert equal, assert true, and assert raises help verify expected outcomes. For example, when testing a function, developers should consider edge cases, such as empty inputs or extreme values, to ensure robustness. This approach helps catch hidden bugs and improves code reliability. Debugging techniques are essential for troubleshooting code. Print statements are a quick way to inspect variable values or program flow during execution. The PDB tool, or Python debugger, allows step-by-step execution, enabling developers to pause, inspect, and modify code dynamically. Modern IDEs like PyCharm or VS Code provide visual debugging tools, such as breakpoints and variable watches, which make it easier to track down issues. Logging is another powerful method, as it records detailed information about program behavior, which is especially useful for diagnosing problems in production environments. Several tools are available for debugging Python code. PDB is a command line debugger that offers basic functionality for inspecting and controlling program execution. execution. IPDB enhances PDB with interactive features such as syntax highlighting and tab completion. PySpy is a profiling tool that helps analyze running processes without modifying the code, making it useful for performance issues. The breakpoint function, available in Python 3.7 and later, provides a modern, built-in way to insert debug points directly into the code. Best practices for testing include writing tests before code, a methodology known as test-driven development. This ensures that code is designed with testability in mind. Tests should be isolated, meaning they do not depend on external factors, and repeatable, so they produce consistent results. Developers should test both typical and edge cases to cover all possible scenarios, automating tests through continuous integration and delivery pipelines ensures that code changes are validated quickly and efficiently, reducing the risk of introducing errors. Common debugging pitfalls can lead to frustration and inefficiency. Overlooking edge cases in logic can result in unexpected behavior, such as division by zero or invalid input handling. Ignoring error messages or stack traces can delay problem resolution, as these clues often point directly to the root cause. Hard-coding values instead of using variables makes code less flexible and harder to maintain. Finally, not using version control to track changes can make it difficult to revert to previous states or understand the evolution of the code base. Testing and debugging are fundamental to creating robust Python code. Frameworks like Unitist and Pytest provide powerful tools for writing effective tests, while PDB and modern IDE debuggers help identify and resolve issues efficiently. By following best practices and prioritizing clean, maintainable code, developers can build applications that are reliable, scalable, and easier to work with over time. Embracing these practices ensures that Python projects remain stable and adaptable in the face of evolving requirements. Virtual environments are isolated Python environments that allow developers to manage project dependencies in a controlled and organized way. These environments act as self-contained spaces where you can install specific versions of libraries without interfering with other projects or the global Python installation. This isolation is crucial because different projects often require different versions of the same package. And without virtual environments, conflicts can arise. For example, if one project needs version 2 of a library and another requires version 3, using a single environment could lead to errors. Tools like Venv, Virtualenv, and Pipeenv are commonly used to create and manage these environments. Venv is built into Python 3.3 and later, making it a straightforward choice for many developers. Virtualenv is an older tool that offers similar functionality, but is useful for Python versions prior to 3.3. Pipeenv is another option that combines dependency management and virtual environments, streamlining the process of handling project-specific packages. By using virtual environments, developers can ensure that their projects are consistent, reliable, and easy to reproduce across different systems. This is especially important in collaborative settings where multiple people might be working on the same code base. Ultimately, virtual environments are a foundational practice in modern Python development, enabling seamless workflows from local development to production deployment. The primary reason to use virtual environments is to isolate dependencies for each project, preventing version conflicts that can arise when multiple projects rely on different versions of the same package. For instance, imagine two projects that both use the requests library but require different versions. Without isolation, installing one version could break the other project. By creating separate environments, each project can have its own set of dependencies, ensuring that updates or changes in one project do not affect others. This isolation also simplifies collaboration. When a team member clones a project, they can recreate the exact environment by installing the required packages, eliminating the "it works on my machine" problem. Additionally, virtual environments help reduce system-wide package clutter. Instead of installing every possible package globally, developers only install what is necessary for a specific project. This not only keeps the system cleaner, but also minimizes the risk of accidental upgrades or conflicts. From a security perspective, virtual environments limit access to global packages, reducing the potential for malicious or unintended interactions. By restricting the scope of installed packages, developers can maintain a more secure and controlled development environment. These benefits make virtual environments an essential tool for anyone working with Python. Whether on a small personal project or a large-scale enterprise application, creating a virtual environment is a straightforward process that begins with a simple command. The most common method is to use the built-in venv module by running the command python mvenvenv. This command creates a new directory called env, which contains a copy of the Python interpreter, the standard library, and other necessary files. This directory acts as a self-contained environment where you can install packages without affecting the global Python installation. For older Python versions that do not include venv, the virtualenv tool is a suitable alternative. The command virtualenv achieves the same result, creating an environment that functions similarly to venv. The key difference is that virtualenv is not included by default in Python versions prior to 3.3, so it must be installed separately. Once the environment is created, the env directory serves as the workspace for that project. It is important to choose a meaningful name for the directory, such as the project name or a brief description of its purpose. This practice makes it easier to identify the environment's role when working on multiple projects. The structure of the environment includes a bin or scripts folder, depending on the operating system, which contains the activate and deactivate scripts. These scripts are crucial for managing the environment's life cycle. By understanding how to create and name virtual environments, developers can establish a consistent and efficient workflow for managing project dependencies. Activating a virtual environment is a critical step that ensures all subsequent commands, such as installing packages or running scripts, use the environment's Python interpreter and dependencies. On Windows, the activation command is env\scripts\activate bat, which must be executed in the command prompt. This command modifies the system's path variable to prioritize the environment's bin directory, making the packages installed within the environment accessible. On Unix-based systems like Linux or Mac OS, the activation command is source env-bin activate. The source command reads and executes the activate script, which sets up the environment's context. Once activated, the command prompt typically displays the environment's name, providing a visual cue that the environment is active. This indicator helps prevent accidental installations into the wrong environment. Deactivating the environment is equally simple and is done by running the deactivate command in the terminal. This command restores the original path and removes the environment's context, returning the terminal to its default state. It is important to deactivate the environment when it is no longer needed to avoid unintended side effects, such as installing packages into the wrong location. By mastering the activation and deactivation process, developers can maintain a clean and organized workflow, ensuring that each project's dependencies are managed precisely. Packaging is the process of organizing Python code into reusable modules and packages, which are essential for creating maintainable and shareable code. A module is a single file containing Python code, while a package is a directory that contains multiple modules and a special init py file to indicate that the directory is a package. This structure allows developers to group related code together, making it easier to manage and understand. Tools like pip and setup tools play a vital role in this process. Pip is the standard tool for installing and managing Python packages, while setup tools provides the necessary tools for building and distributing packages. Packaging is particularly important for sharing code with others, as it enables the distribution of code via the Python package index, or PyPy. PyPy is a repository where developers can upload their packages, making them accessible to the broader Python community. By packaging code, developers can ensure that their projects are modular, scalable, and easy to integrate with other projects. This practice not only improves code organization, but also facilitates collaboration, as others can install and use the packaged code with minimal effort. Effective packaging is a cornerstone of professional Python development, allowing developers to create high-quality, reusable components that can be shared and maintained over time. Key packaging tools are essential for managing the installation, distribution, and maintenance of Python packages. Pip is the primary tool for installing and managing packages, allowing developers to install, upgrade, and remove packages from PyPy or other repositories. Setup Tools extends Pip's capabilities by providing tools for building and distributing packages, including the ability to create distribution files that can be uploaded to PyPy. Wheel is another important tool that provides a built package format, which is a precompiled version of a package that can be installed more quickly than source distributions. This is particularly useful for packages that require compilation, as wheels eliminate the need for the end user detailed tools. PyPy, the Python Package Index, serves as the central repository for public Python packages, making it easy for developers to find and install packages that meet their project's needs. Together, these tools form the backbone of the Python ecosystem, enabling developers to share, install, and manage packages efficiently. Understanding how to use these tools is crucial for anyone involved in Python development, as they streamline the process of working with external libraries and contribute to a more productive and collaborative environment. Managing dependencies with a requirements TXT file is a best practice that ensures consistency across different environments. This file is generated using the pip freeze command, which lists all the packages installed in the current environment, along with their exact versions. By redirecting the output of pip freeze to a requirements TXT file, developers can create a snapshot of the project's dependencies. This file is invaluable for deployment, as it allows the environment to be recreated precisely by running pip install R requirements TXT. The exact version numbers in the requirements TXT file prevent unexpected behavior caused by updates to packages, which can introduce breaking changes. For example, if a project relies on a specific version of a library, the requirements TXT file ensures that the same version is used in development, testing, and production environments. This consistency is especially important in team settings where multiple developers may be working on the same code base. The requirements TXT file also serves as documentation, making it clear which packages and versions are required for the project. By maintaining an up-to-date and version-controlled requirements TXT file, developers can avoid dependency-related issues and ensure a smoother workflow. This practice is fundamental to reproducible development and is widely adopted in the Python community. Adhering to best practices for virtual environments is essential for maintaining a clean, efficient, and secure development workflow. The first and most important practice is to use a virtual environment for each project, regardless of its size. This ensures that dependencies are isolated and does not interfere with other projects or the global Python installation. Keeping the requirements TXT file updated and version controlled is another critical practice, as it ensures that the environment can be recreated accurately. Developers should avoid installing packages globally, as this can lead to conflicts and make it difficult to manage dependencies across projects. Instead, all installations should be done within the virtual environment. Regularly cleaning up unused environments is also recommended, as it helps save disk space and reduces the risk of confusion. For example, if a project is no longer needed, its associated virtual environment can be deleted to free up resources. These practices contribute to a more organized and reliable development process, making it easier to manage complex projects and collaborate with others. By following these guidelines, developers can ensure that their environments remain consistent, secure, and easy to maintain over time. Virtual environments and packaging are fundamental to organized Python development, offering solutions to common challenges such as dependency management, version control, and collaboration. By isolating project dependencies, virtual environments eliminate conflicts and ensure that each project runs in a consistent environment. Packaging, on the other hand, enables the creation of reusable and shareable code, which is essential for both individual projects and collaborative efforts. Together, these practices contribute to a more efficient, reliable, and scalable development process. Whether working on a small script or a large application, developers who adopt these tools and techniques can streamline their workflows and reduce the risk of errors. The ability to recreate environments precisely, share code with others, and manage dependencies effectively is a hallmark of professional Python development. As the Python ecosystem continues to grow, mastering these concepts becomes increasingly important for developers looking to build robust and maintainable applications. By integrating virtual environments and packaging into their daily routines, developers can ensure that their projects are not only functional, but also scalable and easy to manage in the long term. Python packages are a fundamental way to organize and structure code in a reusable manner. By grouping related modules together, packages help developers manage large projects more efficiently. A package is essentially a directory that contains an init.py file, which tells Python that this directory should be treated as a package. This structure not only keeps your code modular, but also makes it easier to share and reuse across different projects. When you distribute a package, others can install it using tools like pip, making their development process smoother and more collaborative. Creating a Python package starts with a well-organized project structure. A common approach is to use a src directory to house all the source code. Within this structure, each directory that needs to be recognized as a package must include an init.py file. This file can be empty or contain initialization code for the package. By organizing your code into modules, which are individual Python files, you can break down complex functionality into manageable parts. For example, a package named My Package would have an init.py file and a module.py file to store its functions and classes. The setup.py file is crucial for defining how your package is built and distributed. This file contains metadata such as the package name, version, and dependencies. The name parameter specifies the unique identifier for your package, while the version indicates its current state. The package's parameter lists all the directories that should be included in the distribution. Additionally, install requires is used to specify other packages that your package depends on. Using setup tools, a modern and widely adopted tool, ensures that your package is built correctly and adheres to current standards in the Python ecosystem. When it comes to building distributions, there are two main types: source distributions and wheels. Source distributions, or SDIST, are platform independent and contain the raw code that can be installed on any system. Wheels, on the other hand, are platform specific and include precompiled binaries, making installation faster. To create these distributions, you run the command python setup.py sdist bdist wheel. The resulting files are stored in a dist directory, which you can then share or upload to a package repository. Understanding the difference between these distributions helps you choose the right format for your audience. Uploading your package to PyPy, the Python package index, makes it accessible to the broader community. First, you need to create an account on pypy.org. Once registered, you can use a tool called Twine to securely upload your package. Twine requires you to generate an API token for authentication, ensuring that your credentials remain protected. After uploading, you can verify the process by installing the package using pip. This step is essential to confirm that everything works as expected and that users can easily access your code. Versioning your package is a critical practice for maintaining compatibility and tracking changes. The standard approach is semantic versioning, which follows a format like major dot minor dot patch. For example, 100 indicates a stable release, while 010 might be an early version. Each time you release a new version, you update the version number in setup.py. Tools like setup tools can help automate this process, ensuring that your versioning remains consistent. Proper versioning allows users to understand the scope of changes and choose the right version for their needs. Managing dependencies ensures that your package works correctly with other libraries. In setup.py, you list dependencies using the install requires parameter, specifying the packages your code relies on. For development environments, a requirements.txt file is often used to track all the necessary packages. For instance, install requires might include requests greater than or equal to 2.25.0 to ensure a compatible version. Tools like pip and Poetry simplify dependency management by handling installations, updates, and conflicts, making it easier to maintain your project. Following best practices when building packages enhances their reliability and usability. Start by documenting your package with a readme.md file that explains its purpose and usage. Include a docs directory for more detailed guides. Writing tests using frameworks like Pytest or Unitest ensures that your code functions as intended. Adhering to PEP 8 guidelines keeps your code clean and readable. Finally, using version control systems like Git helps track changes and collaborate with others, making your development process more efficient and transparent. Several tools are essential for working with Python packages. Setup Tools is the primary library for packaging and distribution, providing the necessary functions to build and install packages. Wheel is used to create platform-specific distributions, improving installation speed. Twine simplifies the process of uploading packages to PyPy, ensuring secure and reliable distribution. Pip, the standard tool for installing packages, makes it easy for users to add your package to their projects. Together, these tools form the backbone of the Python package ecosystem. Building and distributing Python packages is a powerful way to share your work with others. The process involves creating a well-structured package, configuring it with setup.py, building distributions, uploading them to PyPy, and maintaining them over time. following best practices such as documentation, testing, and versioning, you ensure that your package is both reliable and user-friendly. The key steps are to create, configure, build, upload, and maintain your packages. The more you practice with real projects, the more proficient you will become in mastering this workflow. Good morning, everyone. Today, we embark on an exciting journey as we dive into the final project for this Python programming course. The main goal of this project is to build a complete Python application, which will serve as a practical application of all the concepts we've learned throughout the course. This isn't just about writing code. It's about creating a real-world solution that addresses a specific need or solves a problem. Think of it as the culmination of your skills, where you take everything from basic syntax to advanced libraries and bring it together into a cohesive product. The key components of this project will guide us through the entire process, starting with planning and design, moving on to coding, testing, and finally deployment. Each step is crucial, and we'll explore them in detail as we progress through the slides. Let's start with the foundation of any successful project: planning and defining requirements. The first step is to clearly outline the purpose of your application. Ask yourself, what problem does this application solve? Who is the target audience? Understanding these questions will shape the direction of your project. Next, list out the core features and user requirements. This might include things like user authentication, data storage, or interactive elements. It's important to think about what users will expect from your application. Finally, create a project timeline and break down tasks into manageable steps. A well-structured timeline ensures that you stay on track and avoid last-minute rushes. Think about milestones, deadlines, and how to allocate time for each phase of development. This planning stage sets the stage for a smooth and organized development process. Now that we have a clear plan, it's time to design the application architecture. Choosing the right framework is a critical decision. Frameworks like Flask or Django offer different levels of abstraction and flexibility. For example, Flask is lightweight and ideal for small projects, while Django provides a robust structure for larger applications. You'll also need to plan your data structures, modules, and class hierarchies. This involves organizing your code in a way that is efficient and easy to maintain. If your application includes a user interface, sketching out the layout or designing API endpoints will help visualize how users will interact with your application. This phase is all about laying the groundwork for a scalable and well-organized solution. With the design in place, we move on to implementing the core features of the application. This is where the actual coding begins. Start by writing code for the essential functionalities that make your application work. Use functions, classes, and libraries to build these features. For instance, if you're creating a web application, you might use Flask's routing system to handle different user requests. It's important to prioritize modularity and code reusability. This means structuring your code so that individual components can be reused across different parts of the application. By doing this, you'll make your code easier to manage, test, and expand in the future. Testing and debugging are essential steps to ensure your application works as intended. Begin by performing unit tests, which check individual components for errors, and integration tests, which verify how different parts of the application interact. Debugging tools like print statements, logging, or IDE debuggers can help identify and fix issues. Pay close attention to user interactions and edge cases, such as unexpected input or error scenarios. These are often the areas where bugs lurk. By thoroughly testing your application, you'll create a more reliable and user-friendly product. Remember, debugging is not a sign of failure, but a necessary part of the development process. Once the core features are working, it's time to enhance the application with extra features. This could include adding a graphical user interface, integrating APIs for external data, or incorporating a database for persistent storage. These enhancements can significantly improve the user experience and functionality of your application. Optimization is also key here. Look for ways to improve performance, such as reducing load times or streamlining code. Finally, incorporate feedback from testing phases to refine the application further. This iterative process ensures your project evolves into a polished and effective solution. The final phase of the project involves deployment and distribution. Start by packaging your application for distribution. Options include uploading it to PyPI for others to install via pip, creating a Docker container for easy deployment, or generating an executable file for users who prefer a standalone application. Next, deploy your application to a cloud platform like Oz or a local server. ensuring it's accessible to users. Don't forget to provide documentation and user guides, which will help others understand how to use your application effectively. This step is crucial for making your project available to the wider community. To wrap up, let's recap the journey we've undertaken. Building a complete Python application requires careful planning, creative design, meticulous coding, rigorous testing, and thoughtful deployment. Each step of the process has been designed to reinforce your understanding of Python and its applications. Remember, the key to success lies in iteration, continuously refining your work based on feedback and testing. As you present your final projects, I encourage you to share your experiences, challenges, and achievements. This is not just the end of the course, but the beginning of your journey as a Python developer. Keep exploring, keep building, and never stop learning. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of Python will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.